Okay, very good afternoon, all of you, and thanks to Dr. Abhishek for inviting me in such a big event in the EN ICT Academy, IIT Kharagpur sponsored a big program at Chitkara universities. So today means we will discuss the modern deep learning architecture and outline basically why deep learning methods are very much superior in nowadays. In this part, we will discuss in the help of the different types of deep learning architectural models we will highlight and in this short period of time, and we as well as we will discuss some advantage and disadvantage with the different deep learning based models. Deep learning was first theorized in 1980s, but it has only become useful recently because it requires a large amount of label data. We are already familiar with the machine learning, and due to the reducing the burden of data strength, we are moving to the deep learning concept. So it requires the significant computational power, like a high performing CPUs. So average cooling was used in LeNet model, which is the first version of deep learning architecture in 1980s. But AlexNet, an updated deep learning architecture, and adapted max cooling in 2012. But this is another reason for the current deep learning architecture's success. And deep learning is a subset of machine learning that uses the mathematical functions to map the input to the output, and as well as the extracting.
Sir,
Yeah.
only the first page of the presentation is shown modern deep learning architecture. So, are you moving this slide
Yes,
or
yes, yes. No, no, I'm moving.
but the only first slide is shown.
This one.
Uh, okay, sir. Now it is moving.
So these function basically can extract the non-redundant information patterns from the data, and as well as correlation and establishing the correlation between input and output. So this is known as the learning. So process of learning, this is known as the training. And through this training program, we believe that all of you are having a basics or maybe beyond basics level of idea of the deep learning. Just we are the discussing in basics of deep learning, and so that's why this is the one kind of learning process. So here we are applying some input data in the help of some weighting function we have added or normalizing the data. Then some bias because of that, some inability of the model, the summation, and then in the help of the activation function. Activation function means this is the nonlinear function. So nonlinear function means this is, you can say this is the rectified linear unit. Later we will discuss. And here artificial intelligence, this is the big platform, and this is the technique and which enables the machines to mimic the human behavior. And machine learning, this is a subset of AI, we know, and that can be used as a statistical methods to enable the machines to improve the experiences. And deep learning, this is a subset of machine learning, and which make the computation of multi-layer neural networks concept. So why deep learning? Deep learning means this is the some limitations are there of the machine learning you need to find out. So we're not a good at handling the high dimensional data. If you are handling some industrial data or medical data, that means your data volume or data stream is high. So that's why you have to reduce the high dimensionality. This is the one of the major issues. And this is difficult to do feature extraction and object recognition. So that's why we are considering the deep learning. It is computationally expensive and capable of handling the high dimensional data. And feature extraction is done automatically in the help of the means you are applying the data in the input side and you are getting the data at the output side. In between several number of hidden layers are there. So machine learning mainly input, and after that you know that is a feature extraction. Then feature distribution, we can show what are the patterns of the feature distribution. So in that case, you can consider the kernel distribution function also, kernel density function also you can use. And after that, in the help of different kind of classifiers, so we are getting the predictive results at the output end. And deep learning here same case, but scenario is that feature extraction and classification is jointly working because of the data can be processed from one layer to the another layer. And deep learning architecture can be classified in regard one is the supervised learning, unsupervised learning, and supervised learning can be classified in CNN model. CNN means that is a design primarily for the image recognition with the core components. It having the different core components are there. Later we will discuss like a convolution layer, coding layer, activation function, and fully connected layer. That means this is the output layer and dropout. So similarly, the other means important algorithms are there, techniques are there, and classifier is there. So based on our requirement, we need to provide the suitable algorithm. We need to follow the superior but good deep learning architecture. So in that case, different architectures means are there that belongs under the modern deep learning techniques like a LeNet 5, and we will discuss some gist of the AlexNet, JFNet, and GGG16, and Google LeNet, ResNet, ResNext, and as well as your DenseNet also. So many different architectures are there that belongs under the deep learning. So LeNet 5 architecture, and in that case, this is the convolutional CNN architecture. And these architecture can be introduced with several key features and innovations, and it demonstrated the effectiveness of the CNN model. And CNN we discussed that is mainly designed for the image recognition. So that's why LeNet is a pioneering convolution neural networks designed for the digit recognition. It consists of means your convolution layer, convolution, pooling, and hierarchical layers also, feature extractions, and fully connected layers. So, and it was crucial for early breakthroughs in deep learning for computer vision tasks. Okay. So, this is the means your LeNet architecture. And in this LeNet architecture, just you see that is here 7-layer architectures are there. That means your input layer. Input means suppose we are providing 32 by 32 pixel data. That means larger input size means the distinctive features. So and after that we normalize the data. Normalize in terms of what? If we background, that means that is a white color. The white color means this one is 0, and your foreground means this is the black color. So white and black. Second, your layer 2 convolution layer. Here that is a 6 feature maps are included in this section. So each unit connected the 5 by 5 neighborhood. That's why we are getting 28 by 28. That's why it prevents the boundary edges basically. And next, your subsampling layer is there, and after that, your fully connected layers are also involved. So that's why this is the means your discussion like your input layer, convolution layers, pooling layer, and fully connected layer. LeNet have the 3 fully connected layers are there for use for the classification approach, and output layer. This is the program we have done it in that time, that is in 32 by 32. This is the stripe value. 5 by 5 convolution matrix, 6 filters we have considered, some activation function and sigmoid, and output is 20 to 28, 20, 32 we are input, 28, 28. That means that we are preserving the edges. And after that, end of the day, after passing through the set of neurons, layer wise value, chunk 1, chunk 2, chunk 3. End of the day, we are optimize the data, and finally we are getting the output through the fully connected nodes. So what is the advantage of LeNet architecture? This is very much simple, efficient, and proven effective tasks like a handwritten digit recognition and other adaptability, balance, understandability, means basic of the many modern deep learning architecture can use in this granite architecture. Disadvantage, the average pooling was used instead of the max pooling. Pooling layer, that is what do you mean by pooling layer? Pooling layer means it reduces the spatial dimensions to the operation like a max pooling, preserving essential information while lowering computation. So activation function sigma and was used instead of rectification linear unit model. Clear? So in that case, it really ReLU model, that way it returns input value if it's positive, otherwise it returns the zero value. So inefficient for large data set because concept like a cloud was not available in 1990s. That is random forest and SVM has the better performance. Because of that, we are already familiar. And nowadays, you are doing any kind of classification approach or predictive measures like related works, and that time you see that is in all of the maximum most of the researchers are first trying to implement the decision tree and random forest, and after that you support SVM. But they are getting a nearly good result. After that, they are thinking for the deep learning concept. Because of that, for feature training samples, main tricky portion in the coding is one is the training data, another one is testing. So last one is an availability of GPU, which compressionable power of Lanet 5. Next model, this is the AlexNet. AlexNet on the ImageNet large-scale visual recognition challenge in 2012. Model was proposed in 2012 in the research paper named means your ImageNet classification deep learning neural network by Alex. So it consists of 8 layers with learnable parameters, and this model consists of 5 layers. Out of 8, 5 layers are combination of the max pooling, followed by 3 fully connected layers and ReLU activation in each means of those layers except the output layer. Output layer is different. That means this is the fully connected layers. So AlexNet architecture consists of 5 convolution layers, 3 max pooling layers, and 2 normalization layers, and 2 fully connected layers, and 1 softmax layer. So each convolution layer consists of the convolution and as well as nonlinear activation function ReLU that we have discussed. And here input image is fixed due to the presence of the fully connected layers. Next, input size, most of the cases to this value is there, but due to some padding and which is happened works the 2 to 7. So in the last means the Lanet 5, and that time we have discussed due to the preserving of the edges, we are considered 28 by 28. Okay. Next, means this is the architecture. See, same thing, that is here with the input, and this data can be processed from one layer to another layer. And after end of the day, that is by end of the iteration, you need to run the number of iterations are required, and end of the day you have to choose the optimal iteration. That is optimal iteration means in terms of the optimal feature selection scheme. Okay, but I means personally, I have seen that is most of the people nowadays they are having some means hazards type work in the feature extraction. They are not showing any kind of feature distribution map, the highly overlap or less overlap, overlap, or how to optimize the feature. So these are the one of the major area is coming. Because of that, we are having a large set of data, and our objective is that at the end of the day we have to get the better predictive measures. So that's why proper data manipulation, proper data analytics are highly recommended. Okay. So these are the layer because of the from input side, input is the image, and image sizes are there, and then these data can be processed through the convolution and max pooling, and after that they fully connected, and finally we are getting the out. Convolution layer, that is we are discussing the convolution layer. What is the basics of convolution layer? Convolution layer means it applies filters like kernel to the input data and extracting key features like edges, textures, etc. So that's why in that case this is a convolution layer. So mainly extracting the key feature like edges and texture. A pooling layer mainly reduces the spatial dimension to the max pooling operation. Clear? And activation fully active means another point is FC. The FC one. FC means the fully connected layer. It combines features learned by earlier layers to make the final prediction. So same thing we are means we are discussing related, that is what is our objective. Our objective is that is how to improve the accuracy of the model and how to preserve the original information that are coming from means coming through the channel, more means your input side also. So that's why end of the day we have to provide the better accuracy. uh, if you provide the better accuracy, in that case that is you can say our model is running in a good way. Advantage means that is the efficiency, the factor. These are the key parameters. Faster training with the railway activation model, feature learning, effective image feature extractions are possible. Depth, like 8 layers capture the complex patterns, and dropout prevent the overfitting. Dropout means overfitting by randomly deactivating the neurons during the training, and data augmentation is also there. Disadvantage means resource intensive, and another one the large model size, overfitting, outdated, and limited depth. These are the disadvantages of the means AlexNet model. Second means your JetNet model. JetNet, JetNet means this is Bob and Matthew introduced JetNet, and it was slightly improvement of the AlexNet. AlexNet we have studied, we have discussed, and 2013 that is a ImageNet large that is a ILS VRC actually ImageNet large scale visual recognition challenge. This was won by the JetNet and actually visualized how each layer of AlexNet performs and what parameters can be tuned to achieve the greater accuracy. And features, different features, but key features of the JetNet architecture. One is the deep CNN visualization, improve the AlexNet. Mainly, this is the one kind of improvement are there using the ZFNet with respect to the AlexNet. Some adjusted the stride and filter sizes also. Convolution layers, multiple layers for hierarchical features, max pooling layers, fully connected layers, dropout, and enhanced parameter. Actually, this is difficult to discuss in details of the algorithmic point of view. Just I am trying to give some kind of overview. So that's why as for your work, and then in that time you will apply. But just keep in mind the basic features. And this is the general architecture, that is how input image data can be processed from means input layer and through the convolution layer, pooling layer. And after that one, the flattening layers are there. Then 4096 is the neurons. End of the day, we are getting the 1000 neurons are there. So that's why after layer wise, layer 1, layer 2, layer 3 kind of things. So that's why that is a number of features, number of filters are there. So convolution layer are involved in this case. A max pooling layer is also involved. Dense layer is also involved for definite architecture. Same case, this is the algorithmic value, what is the input, size of input, and finally how to get the 1000 neurons through the 8 layer. This is the basic principles that mentioned here. Main advantage is the accuracy and feature visualization, architecture refinement, and regularization, very insightful the understanding. It provided the deeper insights into the convolution neural network functionality and in future adjustment. So that's why again I am saying that is as per your work, that is you need to find out that which architectural model are very much suited for your work. You need to find out. The question is how to find out. That means first of all you need to check your data set. Two type of data set we know, that is one is primary data set, and another one we can generate the secondary data set also. And end of the day you can prepare by, you can design by, you can develop in your own benchmark database. Okay. After that you need to extract the feature value and how many parameters are there. So you need to consider that as much as possible, as much as number of features. If you consider two, three feature value, at the end of the day you are getting a good 95% accuracy. This is not a good one. So my point is that as much as possible, I'll consider at least 5 to 6 parameters. After that, you can analyze, and in that time, you will see some random variation will occur. at the output end. So that in that case, so disadvantage means this is highly computational, and one is the increased complexity and less efficient and potential overfitting. Overfitting is the common issues. So that's why complexity is another issue, and computational time. In practically, I can say that I have faced similar problem for high performance computing facilities are required for getting a means from response using the deep learning architecture framework. Next, another architecture is there. This is known as the VGG, and VGG. This is the another deep learning based architecture. So this is the deep CNN model, the design for the classification tags introduced by the Visual Geometry Group at the University of Oxford, and it is characterized by its simplicity and uniform architecture, making it easy to understand and implement. And mainly it is used for the object detection and classification algorithm, which is able to classify 1,000 images of 1,000 different categories with means accuracy of 92.7%. That is the one of the popular algorithm for the image classification, and is it used with the transfer learning model. I use the one means in one work. You see the deep transfer learning model. If you search, and then this will also be a deep transfer learning model based architecture you design. So that's why your VGG net is a deep convolution network, mainly the simplicity and depth, and featuring in 16 or 19 layers. Okay, 1 6 and 1 6 or 19 layers, 16 or 19 layers. So it uses the small 3 by 3 filters, right? And it is highly influential in improving image classification. So that's why the VGGNet achieved the excellent performance in the year of 2014 ImageNet competition. And in this case, this is means a source image, and this one means your output image. 1,000 neurons concept are there, and in between that is your convolution plus your linear rectification model also associated with this. After that, your max pooling layer, and then your fully connected and ReLU, and after that, your softmax parameter is there. Actually, convolution plus ReLU mean this is the first layer, right? And max pooling mean this is the used to reduce the size, and fully connected plus ReLU mean this is the final layer, right? And after that, this is the soft max. This is the parameter of VGG16 architecture. That is, it consists of 16 layer architecture. That is, I told you that is the one is the 16 layer, another one the 19 layers. The 16 layer architecture it including the 13 convolution layer. So you can see that is C here with convolution 1 to 2. This picture is already drawn. That is, you can see you are applying the data at the input end and output end. You are getting the result at the output end, but in between, that is a 16 layer architecture is there, where 13 convolution layer and 3 fully connected layers is there, and the rest 3, this is the range layer. Main advantage of this model in VGG 16, like on the deep architecture, 16 layers that will capture the complex features. So I told you that is in feature characterize how to you need to characterize the feature value. So maybe simple data, maybe two-dimensional data, three-dimensional data also be there. That's why this means a complex pattern. So how to convert or how to process the complex feature value to the simplify? How to simplify the complex features? How to optimize the features? How to so the different distribution features, different distribution patterns of the features. And simplicity, it uses only the 3 by 3 convolution layers, same case and transfer learning model. It provides this is one of the good option. Because of that, the pre-trained models are available using the means your this transfer learning model. And one of my paper I used the DFNN model, actually deep fit neural net model, using the transfer learning concept also we have applied, and we finally got very good accuracy. And then another point, the consistency and benchmark. I have already told you that for preparing the data set, that is a benchmark database, this is highly recommended for nowadays. And I have seen that is in many journals that is people are working and means people are showing a very good accuracy. You know that is a, means 94, 95. But thing is that when I check minutely at the feature position, feature distribution, in that time I will see the feature sample that is just some few lakhs, 2 3 lakhs data they have considered. So it will be better if you increase the number of feature value. So that's why end of the day that is you can get the better outcome, and that these on that only possible if we design by if we develop the benchmark database. Disadvantages like a computational intensive. This is the means all of the algorithm we have seen that is a computational means computational time and means computational complexity is another issues, and slow training takes longer to train, and due to the depth the slow training. Another one is the large model size. It requires the significant storage space. Storage is the another issue. Another one is the redundant parameters, like it contains the many parameters leading to the potential overfitting. Overfitting is another major issues. Like means we have discussed the overfitting means overfitting model, and it provides the recent sorry the inefficient, not a efficient as more recent architecture like a resonate and efficient net. So another architecture is there. This is known as the Google Net. Google Net, or you can say this is the Inception version one. So Google Net or Inception version one is proposed by research. I think some noise are coming. So just mute your mic. And in 2015, the research paper titled "The Going Deeper with Convolution." Okay. But in this architecture uses techniques such as one by one convolution in the mid architecture and the global average volume value. So that's why in the Google Net Google Net, or you can say this is the Inception Net. So in that case, means the Inception module are there. It combines the multiple convolution filters of different sizes or efficient feature extraction values are there. Parameter reduction uses the one by one convolution to reduce the parameter and computational load. And auxiliary classifiers and your balance architecture is also involved. So that means that is in Google Net, or you can say this is the Inception version one, and this is a means of deep convolution neural networks that introduce the Inception module, and it uses the multiple filter sizes in parallel. This is the parallel architecture you can see from this diagram. That is the input, and this one, this input data can be processed through the Inception cell by Inception version one. After that, is some auxiliary loss, and then end of the day you are getting the final output that are crossing through the auxiliary boxes. So that's why some parallel boxes means it uses the multiple filter sizes in parallel. So features 32 layers are involved and achieves state of the art performance in the 2014 ImageNet competition while being computationally efficient. So that means this is the means your Google Net is the one of the most efficient uh, means your deep learning based architectural model as far this is recognized by the 2014 ImageNet competition. And so in this part we have discussed we had 22 layers and global average pooling, few parameters are involved, and it gives the better efficient and as well as your cost. Yeah.
Excuse me, sir, there is no voice and video.
I think Chinmay sir left the meeting. So we will try to connect.
Is it visible? Hello.
Yes, it's visible now.
Acha, last slide actually I don't know. I will just continue my lecture. Just I have seen that Dr. Abhishek sent the message. Last topic, Google Net. Hello. Hello. हाँ मैं
Yes, sir,
ज्वाइन
it
कर
was
गया
Google
अभी
AliNet.
अभी लास्ट कौन सा हुआ बोलिए मैं अभी ज्वाइन कर गया हूँ ठीक है मैं देख रहा हूँ हेलो इज इट ऑडिबल
Yes, sir, you are audible.
so Google Net I think Google Net is already actually Google Net just I think that is in this portion is okay na No. So Google Net architecture that means Google Net or you can say this is the inception version 1 so Google Net also known as the inception version 1 and this is the deep learning model and this architecture uses the technique like a one by one convolution in the middle of the architecture and global average poolings are involved so it consists of inception module like a combines of the multiple convolution layers of different sizes and efficient feature values are there parameter reduction auxiliary classifier and balance architecture so in this diagram you can see you are applying some value by your input side and this is the final output this data can be processed through the inception version 1 or in inception cell and these layers this data is processed through from one layer to the another layer in between auxiliary loss up there so that's why in that case that is a your Google Net or it's a inception version 1 is a deep convolution neural network that introduced the inception module and it uses the multiple filter sizes in parallel so that's why you see that the multiple filter sizes are there filters are there and it consists of that is a it features 22 layers and it achieved the means your state of the art performance in the 2014 ImageNet competition while being computationally efficient. That means your Google Net is the most means one of the efficient model in the deep learning architecture. So that's why in this part already we have covered like it consists of inception modules, one by one convolution layers, auxiliary classifiers also there, 22 layers are involved. That means you know that is a you can extract the data in deep or better feature extraction values. 22 if data is processed through the 22 layers, that is a, you know that is a, automatically this data will be scrutinized. And last point, this is the efficient means you the high performance in low with low cost. And all of you we agree that is a low cost solution is always highly recommended. And as well as that is a, if it provides the better performance, in terms of the computational complexity, in terms of the computational time. So in that case, that is, you can say this model is the efficient. And efficient and effective model are highly recommended for any kind of industrial and means or medical data. So as per my knowledge, that is, I have seen that is most of the papers I have seen that they have been providing the very good accuracy. You know that it means 94, 95, 96 kind of accuracy. But when I observe that is what are the pattern, what is the feature value, what is the feature distribution, how much overlap, highly overlap, yes, less overlap, no. But this part of the data still missing. That is on few papers are there. But Indian concept I have seen that is whatever as per my knowledge that is people are just concentrating only for how to improve the accuracy. My point is that try to consider number of features, number of parameters, and you can consider as much as feature value. So end of the day, and definitely some variation will be offered. You need to fine tuning some back to front calculation. After that, and definitely you can get the better result. So that's why this is the efficient model used for the computational resources and good performance of the image recognition tasks, and utilizes the deep learning techniques effectively, and it incorporates the inception modules for feature extraction and can be trained and with relatively the small data set. So that's why your training and through the training and testing. In this case, that is you can observe in a very superior way when we are considering the designator ResNet model. And what is the disadvantage? Disadvantage, that is the first part, means disadvantage. One is the complexity of the issue. The complexity of the architecture may be challenging and to understand and implement. Suppose your coding part you are taking means 2 days, 3 days also. So that means you are getting a not a good accuracy. In that point of time, that is you need to focus for your high performance computing facilities required. So nowadays that is all of the institute they are trying to develop some high performance computing systems for implementing the faster communication. So training can be computationally intensive, and overfitting is another issue. Second, it may require fine tuning for specific tags and subsets, and limited interpretability of the internal representations are involved. Another one, this is the race rate. Race rate means after fast CNN model, after fast CNN based architecture like AlexNet, this is the fast model. That we know the ImageNet in 2012 competition. So we mean that it is providing the efficient model. So every subsequent winning architecture uses more layers in a deep neural networks and to reduce the error rate. Suppose you are sending means the image data or any kind of data you are sending, like a multimedia data also. But during the transmission, in that case, you see end of the day you are getting some errors. So that's why how to minimize the error, how to preserve the data, how to preserve the resources. So that's why we know that is means all of you know like pre-processing on filtration techniques, age preserving technique like your color space selection. So many techniques are there. So in that case, that is in race and model. That means this is after the first CNN model, like in AlexNet, and after that is in this model it came into came into the picture for reducing the error rate. And this work for less number of layers are involved. But when we increase the number of layers, so there is a common problem of deep learning associated with that called the means or vanishing or exploding gradient. So that's why minimal number of you need to choose the minimal number of layers. So in that case, that is if you consider the large number of layers, so in that case, some vanishing, exploding issues means will occur. So this causes the gradient to become zero or too large. So that's why increase the number of layers or training or test error rate is also increases. So in the ResNet means the residual network introduced the residual learning to address the vanishing gradient problem in deep learning neural networks, and it uses the shortcut connection of the skip layers and networks to be over 100 layers deep, so while maintaining the performance. And also that is in recent model on the 2015 ImageNet competition and significantly advancing the deep learning method. Okay, so in this figure actually here that is a training area, mainly error that is a 2 layer. This is the number of iterations are involved. So that's why one in the 20, another one the 56 layers are involved in this case. So we can observe that the 56 layer CNN model gives the more error rate on both training and testing data set, right? Compared to the 20 layers data set. So after analyzing more on the error rate, so authors are able to, we are able to reach the conclusion that it caused by the vanishing and exploding gradient. So that's why this is the 56 layer model, CNN model, and another one the 20 layers model also. And so the iteration and training error rate. In this curve, from this diagram, from this figure, you can conclude, okay, it's a 56 layer, it provided the more error rate. So that's why the residual network, so proposed in 2015 by researchers at Microsoft Research, introduced a new architecture called the residual networks. Disadvantage like increased memory consumption due to the residual connection, complexity, the another issues, susceptibility to the overfitting, and training may require the more computational resources compared to the cellular networks. The last one is the potential degradation with the excessively the deep architecture. So that's why you just see that is a memory consumption, complexity, overfitting, and training or computational resources or degradation of the other excessive parameters, the feature values. Next, this is another important architecture like race next. This is the one that means another architectural deep learning architecture, CNN model for CNN architecture. And these were developed by the Microsoft Research and introduced in 2017. Recent actually, recent means at least few years later, before actually. So this paper actually aggregated residual transformations of the deep neural networks. They are proposed, and ResNet repeats a building block that aggregates a set of transformation and with the same topology. And topology means that we know that means it's one of the infrastructure. Like you are sending the data through the infrastructure. And layer 1, layer 2, it consists of several number of neurons, layers. So it compared to the ResNet means the residual network, it exposes a new dimension and the size or set of the transformation as the essential factor in addition to the dimension, depth and width. So this is the architectural model, and here your dimensionality point of view, that is a 128D, and after that this data is processed through the one layer, then your conditionally some value is mentioned, like your 8 layer values is there, and after concatenation, and then we are receiving the 128D data. So main advantage is there, that is a cardinality. That means it increases the number of the parallel paths and group convolutions, like a group A convolution in the parallel. Some residual blocks, like a similar to ResNet, with parallel transformation is there. It provides some efficient or effectiveness in terms of the better performance, and scalability is also involved. And advantageous feature means this provides the better accuracy, higher accuracy than traditional ResNet, efficient scaling, modular design, and effective parallelism, and versatility and easier optimization. And parallelly, for disadvantages are there, like complexity, and complexity means more complex than the traditional ResNet model. So that means that somehow complexity, it gives the better performance, it provides the better or efficient performance rather than the traditional ResNet model, and it requires more parallel computation resources. So that's why I told you that is a high performance computing facilities are highly recommended. And implementation point of view, that is a harder to implement and optimize the practice and increase memory, like a higher memory usage due to the multiple paths and slower the interference, right? And last one, the architecture means now till now we have discussed like a Lenin 5 model and you AlexNet, JetNet and BT16. Some noise are coming. Mute your mic actually.
There is a noise.
And GoogleNet and as well as RaceNet and RaceNext model are also involved. And DenseNet model, next last one, this is the DenseNet. And in this case you see that is a densely connected convolution networks is a family of the convolution neural networks. Again, I am saying that the convolution neural network is primarily designed for the image recognition, and it consists of the important parameters. But components you can say one is the convolution layer, another one the polling layer, another one the activation function, another one is the FC layer, another one the dropout. So that's why this is the one of the, it belongs under the CNN family that uses a dense connectivity pattern between layers to allowing for better feature reuse and the gradient flow throughout the network. That means the well-established pretend CNN model. CNN model architecture widely deployed for the image classification tasks and has achieved the exceptional performances on a number of benchmark data set, so including ImageNet and CIFAR, CIFAR 10 and CIFAR 100. CIFAR means Canadian Institute for Advanced Research. The architecture, DenseNet architecture is based on the series of the dense blocks. It contains the multiple number of convolution layers, and each and every block takes the output of the previous block as an input. Okay, and this architecture is that the feature maps produced by each layer and can be concatenated to form the input to the next layer. That means the output of each layer is the input of the following layers. So DenseNet uses the transition layer between each dense block to reduce the spatial dimensionality and the number of the feature maps. So this transition layer consists of batch normalization. That means your one by one convolution layer and a polling layer. So your architectural point of view, you see that is a DenseNet or means so densely connected network. It improves the information flow by connecting each layer to every other layer in a feed-forward manner, right? So this dense connectivity enhances the feature use and reduces the vanishing gradients and enables smaller and more efficient model. So DenseNet performed well in image classification tasks like a ImageNet. Okay, and these architecture, these are the input, and this data is coming through means your same convolution plus ReLU means your linear means your rectification or rectified linear unit model. That means your linear connection. It returns actually ReLU model means it returns input value if positive, otherwise it's zero. So many layers are involved, and specifically here you see the important concept like growth rate. It determines the number of feature maps output into the individual layer inside the dense block, number one. Number two, connectivity, dense connectivity. That means the dense block, each layer gets a input feature maps from the previous layer as seen in this figure. In this figure means this one, and composite functions and transition layer. Okay. So advantages are advantages of the DenseNet, like the first one, the dense connectivity. Okay, each layer receives the feature maps from all preceding layer and promoting the feature use and combats the vanishing gradients. Okay, in the last algorithm, last deep learning model, I mean, like a race net. In that time we have discussed that is how to I mean, what will happen for vanishing gradient factor. That's why in the parameter efficiency, which is the another part. The fewer parameters are needed and due to the dense connection, so making model in the more compact and easier to train. Next, the gradient flow. Gradient flow means that is a great connection, alleviate the gradient vanishing, and enhance the feature learning schemes. Disadvantage means increase the memory consumption, and due to the dense connection and computational overhead is the another issues and complexity. Okay. So today means we have discussed, just I'm summarizing, today we have discussed the modern deep learning architectural models like LNet 5, AlexNet, and ZFNet, ETG16, GoogleNet, RaceNet, RaceNext, and DenseNet model we have discussed today, and as well as we have highlighted like with the advantage and disadvantages features. But my point is that is as per your requirement, you need to provide the suitable deep learning based architectural model. Okay, thank you. Any doubt or any question? Hello, you audible?
Thank you, sir, for this valuable session.
Most welcome. Or any doubt or anything else?
Madam, I
Then
have,
you can ask me
yes,
now.
sir, I have one. Hello, sir.
Tell me.
Sir, my question is that do you think that every machine has needs some limitation of computing power? So every applications like in case of healthcare area, lot of images contain different type of pixel intensity as well as their modality of capturing the images. So type of applications or type of data we are received in case of healthcare related issues. Machine computing power is obviously plays a major role. Everywhere we may not be have some supercomputing power. Initially we have the images, but we have to try and test it. But kind of accuracy we receive from the deep learning architecture. So, sir, do you suggest any better architecture for healthcare area so that we can place?
Exactly. Exactly. This is thank you very much for your question. Actually, in this same type of question, means we have already faced and we have already facing and we are trying to resolve. We have already resolved in some of the cases. But number one, you need to find out the what type of data set you have. What is the number of training samples? Your number of training samples how much?
Training samples we are receiving a minimum 10,000 because in some case data we are every day capturing different type of images based of the modality of devices. So
But what is the data set means you have taken from means a primary and secondary then benchmark database or you have taken the database from one sources.
sir, it is basically from nursing home or hospitals where people are coming to show their chest, and we are to taking the images if they are suffering from bronchitis or sometimes they are suffering from healthcare blockages or like that. So
So
modality is different because type of capturing images is depend on their particular disease or all these things. So after that, this disease, we are placing these images and in a particular deep learning architecture to extract the accuracy of their disease related to cases. So
yeah,
do you suggest any best architecture for deep learning so that we can place images and checking the accuracy for initial investigation purpose?
now I can see the procedure. Because of that, this is not a doctor patient doctor patient. This is not a doctor patient relation. Okay, that
Yes,
means
yes.
that is a first. I'm just saying the in basic. Actually, this is a hospital. That means clinical information is involved. That means means belongs under the personal health information, right?
Yes,
It
yes, sir.
consists of two parts. One is your clinical information, like your patient history management data, patient data, age, name, and disease history, like this. That means this is the two-dimensional data. One is the clinical information is there, one hand, on the means another hand is this images are there, right? But your point is that is a, how to improve the accuracy in terms of the deep learning model. But my
Yes, sir.
point is the clinical data. Okay, you can set one random means using the rand function you can generate one ID, and respect to the ID, each and every patient can store the data. That means clinical data. Part one is over, and with respect to that ID, image is also be there, and this image can be processed through the different steps like a image pre-processing, uh, then image segmentation, image means feature extraction, then classification. My point, my suggestion is that first you try to implement means your basics, suppose KNN model, suppose decision tree, suppose random forest, and then suppose SVM. After that, you think deep learning. So that's why in that case, you can parallelly you can compare in the machine learning and deep learning. What is the beauty of your right? You just follow the steps actually. First, I'm not suggesting that directly you can go and you can choose. Okay, that is a means you can choose any of the architectural model. This is the most efficient that is in today we have discussed actually, means around eight architectural models, and later probably Mr. Sabyasachi is there from IIT Kharagpur, and he will demonstrate the few algorithmic results. That time you will understand it better. So my point is that is a first go to your data acquisition sector. After that, your pre-processing. Pre-processing consists of color, I mean, color correction, color space selection, and another one is means anisotropic diffusion. And then that means this is the after establishing the pre-processing module, and then go to the segmentation step. Segmentation, and then your feature extraction. After that, your classification. So end of the day, it means you will see that is a, okay. I have used means random forest. We achieved the 91%. After that, this is a step one, and step two, same image data, but you try to collect the more data because of the 10,000 feature value. I don't think that is a. I don't know. Maybe you will get the better accuracy, but thing is that is a, it will be better if you increase the number of feature value at the end, and definitely you will get the better result. But as per your work, you need to find out. This is for training purpose. I don't think that is a, if I say you can use this model, I don't know the what is the data set, what is the pattern of data set, right?
Thank you, sir.
Okay, thank you.
Thank you, sir. Hello everyone, welcome back to another engaging session of our ongoing faculty development program on deep learning applications 2024. It is my distinct pleasure to introduce Mr. Sabyasachi Mukhopadhyay, a PhD research scholar at the Center for Computational and Data Science at IIT Kharagpur, India. Mr. Sabyasachi is not only a dedicated scholar but also the HAAI program administrator at the IIT Kharagpur AI4I CPS First Hub Foundation. With a teaching career spanning over 4 years, he has made significant contributions to the academic and research community. He holds an Indian design patent and has authored 40 Scopus indexed papers and 11 research articles in the international journals. His work has been presented at 31 international and 7 national conferences, underscoring his active engagement with the global research community. He has also supervised 26 postgraduate students and published 4 books reflecting his commitment to fostering new talent in his field. He is a Chanakya PhD Fellow recognized by the IIT Kharagpur and has delivered invited talks at more than 130 national and international seminars, workshops, conferences, and events, including over 25 faculty development programs. Today, he will lead a practical session titled Hands on Training on Modern Deep Learning Architectures. This session is designed to provide participants with practical experience and insights into cutting edge deep learning technologies that are shaping our future. Sir, over to you.
Am I audible clearly?
Yes, sir.
Okay, so thank you very much to the organizing committee of Chitkara University for inviting me as a guest speaker. I am thankful to them. And already Dr. Chinmay Chakraborty from BIT Mesra has taken a very beautiful session on the modern deep learning architectures. So already you have got some idea of the modern deep learning architectures, which includes the AlexNet, VGGNet, ResNet, etc. So today I will show you some of the hands-on demonstrations, which are the essential part for the deep learning executions, and it will be useful for enriching your knowledge and applying it for your research papers or writing company white papers. So it will be quite useful for that. So if you check the comment box window, my GitHub link has been there. I have posted it in the GitHub link. So you can follow my GitHub for further update on the coding part. And also I am sharing the specialized repositories, first of all, for the AlexNet. Okay. So first we will execute the AlexNet and then we shall move towards the VGGNet. Okay. So let me share the individual repository link to you as well, so that it can help you in terms of the execution of the code part. Okay, so already I have posted the AlexNet. Okay, now I am going to post the VGGNet. Just check it out. So this one is for the VGGNet, the next one which I have posted here. Okay, so 2 links have been posted, one for the AlexNet, another one for the VGGNet, because this is the 1 hour hands-on session. So these 2 will be adequate enough to cover the entire time given for the session. And those who are interested to make their career in the AI or this type of the domain, for them I am also sharing my Medium articles account. So there I write the Medium articles to guide the professionals in terms of enriching in their career. So this is my Medium profile link. If you wish, you can follow me in Medium. Okay, and this is my YouTube channel link. Okay, so there I share my talks and the invited talks and all the hands-on sessions. So you can access those resources from my YouTube channel as well. Okay, so this is my YouTube channel link. So all the resources I have provided. Now, basically what we will do, for today's session, we will use the Google Colab. Okay, so how to use that I am going to show you by sharing the screen. Okay, so first of all, simply search in Google Colab. Just a second, let me share the screen with all of you. Acha, moderator, can you please allow me to share the screen? Please allow me to share the screen. I have not been allowed to share the screen. Thank you so much for making me co-host. So you see in the screen, it is visible, I hope, that just search in Google Colab. Okay, so I am waiting for all of you. It's now 11:51. Uh, 11 and click on the new note. Click on the new notebook. Once you open up the Google Colab, so click on the new notebook. Okay. So please get ready. Open Google Colab and get ready. Okay. So it's now 5:11. I am waiting 1 more minute for all of you to get ready. Okay. So what I will do, I will explain the concept. Okay. For the continuation purpose, I will highlight the background, BIP theoretical background. Then I will explain the coding part, and I will share the code with you, and you please explore with me. Those who have already access in my GitHub, I have shared the GitHub link as well, so they can reproduce the result with me. Okay, from the GitHub, following the GitHub, and those who don't have the GitHub access, they just see how I am executing it. Okay, so I can post the code chunk of the codes in your comment box, so you can execute one by one with me. Okay, so please get ready with Google Colab. I am waiting here. Okay, so this type of the node feature will come up. So you can put some name, like for example, demo 3, like demo 3. For example, I am saying you can keep it some name like demo 3. Give some name. Okay. So I believe all of you are ready with the Google Colab. Now let us go back to the original notebook. So this is the AlexNet notebook, which I am going to discuss today. Okay, so this is the notebook where I am just showing you two things, important part. Those who are new to Colab, for them, this is the plus code button. Okay, so you can write some code there. Write some code, and this is the run cell button. After the code, writing the code, you can execute by clicking on the run cell button. And the plus text section is there. You can add up some text wherever required. Okay, so for example, if you see my original Python notebook, there are some text I have added. Okay, for your understanding purpose. Okay, so that you can get the BIP background. So there, all the BIP backgrounds have been given there. Where do we land up to the AlexNet? So before we start the hands-on, I am just taking a couple of minutes to explain the background, how it is happening. Okay, for the AlexNet purpose. So you see, like already Dr. Chakraborty has already highlighted the important part. So although the mathematical development of the deep learning took place in 1980, and under the, for example, Ian LeCun also led with the LeNet architecture, but there were certain limitations, because you see during 1980s you don't have this type of the data which we are facing nowadays. We are facing with the most of the cases unstructured and the semi-structured data, but in those cases we have seen the data which were basically from the structured data set. Okay, so in those days people relied on the SQL and the RDBMS mainly. Okay, in those era, okay, you don't have the data like so many humongous data like these images or videos, which started when we came up into the era of the 1990s. Okay, gradually due to the social media, arrival of the social media, whether it is Facebook or, for example, LinkedIn later on, whenever you are posting something. So for example, if you are posting some text, images or video, these are the unstructured part, and your login time and the logout time, these are stored in a structured manner, tabular format. So holistically, you are generating the semi-structured data for your activity in Facebook, Twitter, or LinkedIn. Okay, so nowadays, because of this reason, you can see there is an exponential growth in the digital database. Okay, so nowadays the number of the stars in the universe is equal to the number of the bits in the digital world, right? So because of that reason, the pattern of the data which we are dealing with nowadays, it was not the same during 1980s when Ian LeCun came up with the LeNet framework. So in 1980s, the mathematical development has happened. Basic architecture of the deep learning was formed, but the performance of the algorithm failed in front of the machine learning. In those eras, support vector machine, addition trees, random forest has the huge popularity in those era, and because of those reasons, deep learning does not perform as expected. Okay, but it's thanks to Fei Li. Okay, she understood the reason behind the that particular case, because you see now in that era you don't have the cloud to store the huge data. First of all, you don't have GPUs. The second problem. Third problem was that definitely, for example, in case of the linear architecture, okay, average pooling was used. Okay, max pooling was not used, and activation function sigmoid was used. ReLU was not used. Okay, so ReLU, concept of the ReLU has been explained by Dr. Chakraborty. So you have seen that sigmoid or tan hyperbolic are not performance-wise scalable, which we have seen during the machine learning. But ReLU activation function rectified linear is the performance-wise scalable. You have the performance-wise scalability, which actually helps you. This type of the nonlinear function, which actually helps you to deal with the nonlinearity in the network. Okay, which can enable you to deal with the complex representations. So those things were not there earlier. So these are the beauty of this present architecture, and due to that reason, AlexNet in 2012 were able to beat LeNet. Okay, so which were not possible earlier, that we have seen so far. And definitely let us now see one by one that how we can explore one of the reproduction of the result in terms of this AlexNet. So if you see general comparison here in the screen, so basically in the LeNet we have seen, like I mentioned, if we look at the LeNet, so for example 28 by 28 input image. Okay, so here you see there are basically two convolutional layer, 5 by 5, two convolutional layer, followed by two average pooling layer and three fully connected layer. Okay, so this was the general architecture of the LeNet. So LeNet was used basically for the hand digit recognition purpose. Okay, so that was the main function of the LeNet, and already you have seen the utility of those layers. What are the function of those layers? In convolutional layer, what do you do? Basically, with the help of the kernel or filters, what you do is basically extract the complex features during the execution of the learning architectures. And the pooling layer, mainly its task is to reduce the computational cost. Okay, so that is the main function of the pooling layer. Already I have told you what is the function of the activation function. And fully connected layer, what does it do? It combines the features. It combines the features, okay, so that from the earlier layers for making in terms of the final prediction purpose. Okay, and we can see some of the use of the dropout layers during our execution. Okay, so dropout layer, what does it do? It basically avoids to help the overfitting phenomena. Okay, so this is basically the comparison of the LeNet and the general comparison of the architecture of the AlexNet. So you see 224 by 224 with 3 channels were there, and there are, you can see 1, 2, 3, 4, 5 convolutional layer. Okay, followed by their corresponding max pooling layer and 3 fully connected layer. Okay, so this is the general structure of the AlexNet. Now let us go to one by one execution of the entire execution of the coding portion. Okay, so here we are using one of the important framework, that is the MXNet framework. Okay, like TensorFlow or PyTorch, MXNet is another beautiful framework for executing this kind of DI algorithms. So first pip install will execute the MXNet. Then we will install the D2L, which is the deep learning supportive framework. And then from MXNet, we will import NumPy. All of you know NumPy is important for the array execution, array operation execution. And NPX makes it the version independent. Okay. And then from MXNet.gluon, we will import the NN. So gluon is very important in terms of this speed up the entire neural network execution process. And then from D2L, we will import MXNet as D2L. Okay. And then finally, we'll make the setup. Okay. And let me explain the entire thing, and then you will do the execution of this part. So once this setup is done, what we will do, we will make net which will be assigned to nn.sequential layers. Okay, so sequentially one by one execution will be done. So first step, what we will do, we will use define the window size, larger window, for example, 11 by 11 window to capture the object. Okay, so here we will keep the stride as 4, okay, which can help us to reduce the height and width of the output, keeping the stride 4. And then what will happen, it will make the number of the output channel is larger than the LeNet, okay, which we have seen so far. So in that case, what we will do, net.add nn.cont2d. Okay, so first argument 96, kernel size we are mentioning 11. Okay, we are making the stride 4, and the activation function is ReLU. Okay, rectified linear unit. And then as we are replacing the average pooling operation with the max pooling operation. Okay, so in the max pooling case, what we'll do, we'll put the pool size equals to 3 and stride equals to 2. Okay, so once this is done, the next step, what we are doing, basically coding part, I am explaining one by one. So you can see for your understanding purpose, not only the theory, I have also highlighted this comment. Okay, each line of the cases, what is happening for your understanding cases. So once this will take place, okay, so then what will happen? We will make the padding. We will put up some padding in the next step. So NNCon 2D 256 kernel size we are keeping 5, and then padding 2 for the making certain consistent. Okay, because to make the convolutional window smaller, so that's the reason we are putting the padding equals to 2. Okay, then activation equals to ReLU. NN max pool 2D, we are putting pool size equals to 3, stride equals to 2. Okay, and then what will happen? Using of the 3 successive convolution layer, because there are total 5 convolution layers. So first 2 layer I have explained, corresponding their max pooling layer, and the next part what will happen, 3 successive convolutional layer. Okay, so will be there. So first of all, NNCon 2D. Okay, so what will happen in that case? 384 will be the first input channel number, then kernel size 3, padding 1, activation equals to ReLU. NNCon 2D, okay, 384 total channel number, then followed by your the kernel size 3, padding 1, activation ReLU. Then again NN.con 2D channel number 256. Okay, then what will happen? Kernel size 3, padding 1, activation equals to ReLU, and then one corresponding their max pooling layer, that is NN.max pool 2D, pool size will be 3, stride 2. So what will happen in that case, that the number of the fully connected layer which we'll see, it will be the several times larger than the lanet which we have seen so far. And I told you that dropout we are going to use to reduce the overfitting phenomena. Okay, so in that case, what we are doing in the dense layer, NN.dense, okay, 4096 channel number, along with the activation, we are keeping ReLU, and NN.dropout 0.5. Okay, so it will reduce the amount of the complexity present in the entire architecture. Okay, then NN.dense 4096 activation ReLU, NN.dropout 0.5, and finally, okay, so basically fashion MNIST in generally has the 1000 classes in terms of the prediction, but here we will only deal with the 10 classes to reduce the computational time. So that's the reason NN.dense will be 10. Okay, so this is the entire part which I have explained in front of you. Okay, what we are doing in the first section. Okay, now let us reproduce this portion of the result in the comment box. In the just a second. So basically demo 1 window. So here you see in the demo window I am reproducing the result. So there you can check out. Also, let me try to put it here in the comment box section as well, so that those who are unable to use my GitHub, for them I am keeping it here. So check in the comment box. I am posting it there. Just a second. So some portion of the code has been delivered, few portion is remaining. So let me stop screen sharing and post the remaining part. So part by part I am sharing. Okay. So put all those parts in a single cell like I have done. Because due to the watt limitations, the entire chunk of the code will not be able to give there. Okay. So those who are directly accessing my GitHub, they can access it from there. Otherwise, follow the codes which I am posting in the comment window. So last which I posted there, that is nn.dens4096 activation relu. Now put this. Okay, so entire part I have shared in part. So let me go back to the original notebook. Just a second. So those who are using my GitHub or unable to track my GitHub, for them AlexNet part I have, this is the link of the AlexNet repository. Okay, so you can use it as well. So I have reposted it again. I posted earlier, I reposted it again. So I am using this now. So those who are getting runtime error, please terminate the other sessions. Okay, only activate the runtime for this session. Okay, so in this way you will be able to avoid the runtime error. Okay, so I have seen that a few of you posted the runtime error. So please turn off the other runtime to get the benefit of the present runtime. So this is, you see, reproduction of the first cell, okay, which we have executed here. So this is the first part. Okay, so this is the first part we executed successfully. So once you are done with it, please write in the comment window at least three or four participants. If you make it mark as done, then I will proceed to the next part. At least 2 or 3 volunteer answer will be helpful for me. So, so I got already 3-4 answers. Thank you so much. Thanks a lot for your precious help, because it's an online session, so your cooperation is sought for. Okay, so now let us move to the next part. Let us move to the next part. So once we are done with it, next part, what we'll do, we'll construct a single channel data example, okay, with both height and width will be 224. Okay, to observe the output shape of each layer, and it can match the AlexNet architecture. Okay, so which we have shown here in figure 2 means this particular architecture figure. Okay, so that we have to follow. Okay, so this particular architecture figure where we have seen the comparison between LeNet and AlexNet. In this case, we have seen the 5 convolutional layer followed by 3 fully connected layer. Okay, so this particular segment, if you see in this case, so what we are going to do now, we are going to form it. So basically, to form that np.random.uniform, where we will assign the size 1, 1, 224, 224, and the net.initialize for layer in net, capital X equals to layer X. Okay, print dot layer name. So layer dot name output shape with, okay, and the tab, it will keep on printing all the corresponding output shape of each of the layer along with the layer name. Okay, so Python is a zero indexing language, so it will start from const 0. Okay, so const 0 output correspondingly pull 0 output shape. In this way, you will see up to 4 it will go on. Okay, and then dense layer output, okay, dropout, because we have used the dropout layer for avoiding the overfitting, that will be there. Okay, so dense 0, dense 1, dropout 0, dropout 1, and the final outcome of the with the classification result of the 10 classes. Okay, so that will be given at the dense 2 output shape with 10. Okay, so that we can execute in this particular segment. Okay, so this is a small chunk of the code. I hope it will not be problematic to share the entire code in one shot in the comment box section. I think it will be done. The entire code, I think, posted there. Okay, so this is the small chunk of the code. So it's now 5:32. Please finish this portion within 1 more minute. Okay, by 5:33, then we shall move ahead for the next part. Okay, so I am just let me also put it in the demo window as well, so that I can show you the reproducibility of the code. Okay, so as you can see, the codes are reproducible. Okay, it is running successfully in the demo window. Okay, so I'm explaining the each step. I have already explained the theoretical background, why we are doing this. That is also important. Why LeNet did not work and why does AlexNet work? I explained again. Okay, and then I am giving you the hands-on demonstrations so that you can understand each and every step. Okay, so once you finish this, then we shall move to the next part. Okay, so I will wait for a few more seconds, and then we will go for the next executional part, reading the data set. Okay. So let us move towards the next step. So reading the data set, what we are going to do here. So basically what happened that it was trained on the ImageNet in the paper. Original paper, it was trained on the ImageNet. But what we are doing, we are using instead the Fashion MNIST. Because the ImageNet model will take more time to converge. Okay, it will take some several hours or even some day as well on a modern GPU even. Okay, so what will happen to avoid this particular problem, we are basically taking the Fashion MNIST. So this Fashion MNIST images have the lower resolution, 28 by 28 pixel. So what we will do, we will basically upsample them. We'll use the upsampling process to make it 224 by 224. Okay, and that can be done by using the resizing operation. Okay, so batch size, what we are doing, we are keeping it as the 128. Okay, so the d12.load data fusion MNIST, Fashion MNIST, what we are doing, we are keeping the first argument as the batch size. Okay, first argument will be the batch size and second argument resize will be 224. Okay, and we are assigning as the train item, test item. Okay, so this we are executing here. Now this is a small chunk of the code. I think one shot I can post it in the comment box window. It can be done. Okay, so thank you so much. Voluntarily I got some answers. So I request every time during each cell successful execution, please at least 2 or 3 people please voluntarily write there done. So it will be easier for me, because I know there are nearby 100 people who are attending, including respected professors and students. So I'm requesting them to kindly cooperate. So thank you so much for your cooperation. So this is the part, please you execute here, and I am also keeping it in my demo window. So you see this, whenever this green tick is appearing along with the execution time, that means it is done. Okay, so in few cases you may see 5 seconds, 9 seconds, 0 second, that type of the timer. Along with the timer, this green tick will appear. Okay, for the successful cell run. Okay, so please let me know once you are done with it. Okay, so it's 5:36. I'm requesting everyone to complete this portion by 5:37 so that we can move to the next part of training part. Okay, next part will be the training part. So I already got 2 answers. Thank you very much, those who are giving me the answers. Done. Please, I am waiting for another 1 or 2 done. Then I will move to the next part. So in the next part, in the training part, okay, so what I will do, we will see that we can start training the AlexNet. Compared to LeNet, the main change here is the use of the smaller learning rate and much slower training due to the deeper and wider network, okay? Because the higher the image resolution, the more costly will be the convolution. Okay, so here what we are doing, we are keeping the learning rate 0.01 and the number of the epochs we are keeping as 10. Okay, so in that case, D2 doll train, what we are keeping here, then the first argument will be the net. Okay, second argument will be the train iter, third argument will be the test iter. Already those things we have assigned earlier steps. Number of the epochs, okay, and then okay, the learning rate. Okay, now once we execute this particular portion, it will take some time. Let me tell you, it will take some time for the execution. So once the successful execution will be done, you can see over the number of the epoch, as the number of the epochs is increasing, as you can see, the training loss is reducing. This blue line, which is indicating the training loss, that is reducing, as you can see in the screen, and the training accuracy, which is given in the for the training accuracy, and the test accuracy is also indicated with the green dotted color. These are increasing. Okay, so training accuracy also and test accuracy, both the cases for the training data set and the test data set, both are increasing, and the training loss is reducing. Okay, so you can see over the training data set, the training accuracy is 87.9%. Okay, and the test accuracy is 88.6%. Okay, so very good accuracy. Over the period of time, the more the number of the epoch increases, training loss reduced and training accuracy and test accuracy increased. Okay, so this particular portion, it will take some time for the execution, I repeat. So within this session, it will not be possible. I can show you, you can consider my notebook as a reference book where you can cross-check the result, which will be reproduced later. Okay, so just keep on running and open up the new demo window. Okay, for the VGGNet. So after the AlexNet, we will move to the VGGNet. Let's keep it run. Okay, and open up a new demo window. Okay, so to conclude AlexNet, okay, so once you successfully execute it, I repeat, you will get this following accuracy. We are printing the training and test accuracy together. For example, in my case, I got training accuracy 87.9%, test accuracy 88.6%. So test accuracy is giving better result than the training accuracy. So there is no overfitting scenario. Okay, so if the test accuracy and training accuracy varied much, then there can be the sign of the overfitting, but this is not happening there. Okay, so in a nutshell, what I can say that in summary, as you can see, the AlexNet has a similar structure of LeNet, but uses more convolutional layer and larger parameter space to fit the large scale ImageNet dataset. Okay, today AlexNet has been surpassed by much more effective architecture, or definitely, for example, the VGGNet, ResNet, okay, InceptionNet, ExceptionNet, those advanced architectures are also available. And also, it seems that there were a few more lines in the AlexNet implementation than the LeNet. It took the academic community many years to embrace this conceptual challenge and take advantage of the excellent experimental result. Okay, because in those era I mentioned that computational resources were not available that much, and obviously dropout, ReLU, and pre-processing were the other key steps in achieving the excellent performances, okay, in computer vision task. Okay, so this is the overall coverage of the AlexNet. Okay, I will share this particular notebook with the organizers, and already those who are accessing my GitHub, they have directly explored this AlexNet notebook. Okay, so they already know that. So we shall move to the next part, that is basically dealing with the VGGNet. Okay, so those who are getting ready, please open up the new Python notebook, okay, for the next demo window, where we shall explore this VGGNet part. Okay. Okay, so now please get ready with the VGGNet. We're going to discuss with the VGGNet. So please open up a new notebook. You can give some name like demo 2, demo 3, whatever you may wish. Give some name there. Okay, and let us explore this. So this is the notebook window for the VGGNet. So let me repost the VGGNet with you, VGGNet GitHub link with you. Just a second. Let me post in the comment box. So this is the link for the GitHub link for the VGGNet. So I have reposted it. So those who are keen to follow, please, you can directly access it from there. So please check my comment. Okay. So the limitations of the AlexNet, we have to first know. So the limitations of the AlexNet, what we have seen, that AlexNet is the benchmark for starting the deep learning era, because I told you that LeNet did well at that period of time, as machine learning algorithms have overshadowed it. But for the data in order of 10 to the power 5 or more, okay, we have seen the beauty of the scalability in terms of the performances for the activation functions like the ReLU, and we have seen the effectiveness and the beauty of that application in case of the AlexNet. But the AlexNet, what happens that if you want to get a general template for your own architecture design, for example, those who are the regular researchers in this field, they have to come up with new architectures. They have to build new architectures, and for that, a general template is very much important for designing that kind of the new networks. Okay, so keeping that concept in mind, okay, so Visual Geometry Group, VGG, okay, at the Oxford University, so they came up with a general template, block-based approach in the modern deep learning architectures, so that the concept of the VGGNet coined up. Okay, so if you see the VGG block, so in general, what happens that the basic building block here, we will see some of these simple cases. So first of all, a convolutional layer will be there with padding to maintain the resolution. Second one will be the ReLU. So can you please mute, madam? So the sound is coming, unnecessary noise is coming. Okay. So I am requesting all the participants to keep themselves mute because some unnecessary noise is coming. Okay. So the next is the non-linearity such as ReLU. Okay, ReLU is also there, and the pooling layer such as the max pooling layer. Okay, so one VGG block can consist of a sequence of the convolutional layer. Okay, and followed by the max pooling for the spatial downsampling. And then if you see the original paper, which was published in 2014, because AlexNet was the winner of the ImageNet competition in 2012, whereas the VGGNet was the runner-up in 2014. Okay, so it's also a very useful concept we can see. So we will use a very interesting function. We'll define interesting function, that is VGG underscore block. Okay, to utilize this VGG block. So for example, let us start this particular case. So pip install AlexNet, which is one of the important framework for the deep learning architecture. Then pip install D12, which will also supportive framework for the execution of the deep learning code. Then from ImageNet import np, npx. Okay, already I told you numpy, which is basically the abbreviated form. It is written as np, very much important for the array operation. Npx is a version independent cases where you can execute the NumPy very easily from mxnet.gluon import in. So I told you that to speed up the neural network process, you are using the gluon here, and from D2L import mxnet as D2L, and the next step, as usual, the npx.setup, and under that you are defining the block-based architecture. So here you can play around with the number of the layers. So for example, VGG 16, VGG 19, by enhancing the certain amount of the convolutional layer of the corresponding fully connected layer. So you can play around those layers, number of the layers. So defining the VGG underscore block, first argument will be the number of the convolutional layers, second argument will be the number of the channels. Okay, and then in-sequential. Okay, so you can assign it as the block. Okay, and then for in range, you can execute the for loop here, where the argument will be number of the convolutional layer, and then keep on adding the blocks. So blk.add. Okay, con2d, first argument number of the channel, kernel size is 3, padding is given here 1, and the activation is the rel. Okay, and then blk.add max pool 2d, so pool size is 2, stride 2. Okay, and return block. So this is the code explanation what we are executing here. So I am just putting this particular code in my demo window for the reproduction purpose. Okay, so those who are accessing my GitHub, please reproduce this result, and also I am posting it in the chat window. I think the entire portion of the code has been posted there. Okay, so return block, till return block, it has been posted. Okay, so execute it, and once it is done, just let me know with your comment. Okay, so it's now 5:47. So please finish this by 5:49. And as I mentioned that I will, apart from sharing my this GitHub link, those who don't have the GitHub account, they are accessing the code from the comment box. For your assistant purpose, what I will do, I will email these two notebooks to Dr. Abhishek so that he can share with all the participants. Okay. So not only you can access the codes, but also the relevant theory portion has been added there in the notebook, so you can easily access them, and you can understand what are the advantages and the shortcomings of these two architectures, which we are covering today during the hands-on session. Okay, so one comment I got answered. I am requesting other participants also, please write here. Okay, so I will wait for one more minute and move to the next part. Okay, so another answer I got. Thank you so much. It's good to see that all of you are actively participating in the hands-on session. So that gives me a great pleasure. So thank you so much. Okay, for your precious comments. Okay, so another response I got. So let us go back to the original notebook and execute the next part. Okay, so once it is done, now let us move to the next part. In the next part, what we are going to do, we will see in general VGG network, what happens that like the AlexNet or LeNet, it also has the two parts. Okay, first consisting mostly of the convolutional pooling layer, and the second part it has the fully connected layer. Okay, so in the convolutional part, network connects the several VGG blocks together. We have seen the VGG underscore block function in the succession, and following the variable, we also have talked about the convar. Okay, which consists a list of the tuples one per block. Okay, and each contains the two values. First of all, the number of the convolutional layer. Other one is the number of the channels. Okay, so if we see the original VGG network, it had the 5 convolutional block. Okay, so among which first 2 have the 1 convolutional layer, and the latter 3 contain 2 convolutional layer each. Okay, so you can see in general, for example, if I show you the VGG 11 case. Okay, so this is the block-based architecture, and within the block you see this is the VGG block. Okay, so for example, if there are 8 VGG convolutional layer and 3 fully connected layer, it will be VGG 11. Okay, if there are 13 convolutional layer and 3 fully connected layer, that will be VGG 16. So in this way, you can play around with the block with the number of the convolutional layer, and you can form your own VGG block. Okay, VGG network, VGG, for example, VGG 11, VGG 16, VGG 19. So this is the comparison between the AlexNet architecture and the VGG architecture. Okay, with the block-based. Okay, So now let us move to the next part where we are going to have the idea of the implementation of the convolutional architecture. So this is a very small chunk of the code. Let me post it in the comment box section so that you can easily reproduce it. And also I am keeping it in my demo window for the successful execution purpose. Okay, so let me try it out. So if you are checking the runtime error, so please turn off the other sessions. Okay, please turn off the other session, terminate the other session, so you will avoid the runtime error. So let me post it in my demo window as well so that I can run it successfully. Those who are done with it, just write in the comment box done so that I can move to the next part. So this particular section, you can see I have been successfully implemented this particular part, conbark. So let me check some of the comment box chat. Okay, done. 2-3 examples I got. Okay, who have said that they have been able to complete it. So let us move to the next part. Okay, so now what we will do, we will use the code implementation of the VGG11. So def VGG conbark will be the first under this particular defining of the function. We are giving this convolutional architecture as the input. Then net equals to nn.sequential. Then the convolutional part, what we will do, we will put the for loop. So for number of the convolution layer, common number of the channels in the conbark, net dot add VGG block, number of the convolution and the number of the channel. So these two will play around in the convolutional block, because if you see general structure of the block, so this is the VGG block, okay, where you are playing around with the number of the convolution layer. Okay, depending on that, we are giving the names of the VGG 11, 16 or 19. Okay, so then fully connected layer will come into the picture. So nnet dot add nn dot dense 4096 number of channels, followed by the activation ReLU and the dropout layer, like we are keeping 50% dropout, so 0.5 will be there. nn dot dense, same thing, 4096 channel and the activation ReLU, nn dot dropout 0.5, and the output will be 10. That's the reason nn dot dense 10 and return net, and we are finally assigning net equals to VGG conbark. Okay, so I am putting this portion in the comment box section for your successful execution purpose, as well as I will run it in the demo window as well. Okay, so I am putting it in my demo window, okay, for this successful execution as well. Okay, so you see it has successfully run. It has successfully run. So in your case, it will also run. So let me know once you finish it. Okay, so I will move to the explaining of the next step. Please acknowledge in your comment box. Okay, so already 2-3 answers I got. Thank you so much. Good to see that you are seriously executing these codes. Now let us move to the next part. So now we will construct a single channel data example with a height and width of 224 to observe the output shape of each layer. So net.initialize, okay, np.random.uniform size 11 224 224. Then for BLK in net, x equals to BLKX, print BLK.block name. BLK stands for the block name. Print output shape, okay, and shape.x.shape. So you see, like in case of the convolution, AlexNet we have done, VGGNet we are also doing it. So each of this layer name and their shape will be printed successfully. Okay, so this is the way of printing the output shape of the each layer. So you will get the clear idea of the output shape of the each layer. So I am posting it here for your understanding purpose. So entire code chunk of the code has been posted in the comment box, and I am showing you the reproduction of the result in the demo window. Okay, so please, like every cases you are doing, let me know once you are done. Okay, so you see it has been successfully executed along with the layer name and their shape. Okay, just let me know once you are done with it. Okay, then we shall move to the training part. Okay, so I got the answer. Thank you so much. Done. Okay, thank you so much. Already the results I have seen. So let us move towards the training part. We are almost towards the end of the session. So let me just show you next part, that is the training. So since VGG11 is more computationally heavy than the AlexNet, we can construct a network with the smaller number of the channel. So what we are doing, we are defining the ratio equals to 4 and the small convert, okay, pair 0, pair 1, okay, and then what we are doing, we are putting the pair in convert, executing the for loop, and then VGG function we have applied over this small conv architecture and assign it as the net. Okay, so this chunk of the code I am posting in the comment box, and also showing it, putting it in my demo window. Okay, so as you can see, it has successfully run. So you can also see in your notebook it will run so far. So just let me know, then I will show you that by slightly changing in the learning rate. Okay, how can we execute the entire portion with the number of epoch? How the training and test accuracy can increase. Okay, so already I got some of the cases done. Thank you so much. Done. Okay, fine. Thank you so much. So now let's move to the next part. That here also it will take a lot of time to execute this portion. So if you execute successfully, it will be this type of the shape will come up. Okay, the final step. So learning rate we are keeping 0.5, number of epoch 10, batch size 128. So you can resize it as 224. First argument will be the batch size, second will be the resize, and then you just run over the net train iter, test iter, number of the epochs will be there along with the learning rate. So after the successful execution, you see over the same data set in comparison to the AlexNet, VGGNet, you are getting better accuracy. AlexNet, you may remember, you have got 87.9% in the training accuracy. Here you see in case of the VGGNet, you are getting 93.5. Okay, in the AlexNet training test accuracy, you got 88.6%. Okay, here you got the test accuracy for the VGGNet 92.7%. So much better accuracy than the earlier cases. Okay, so this part I am posting it in the comment box section. So just execute it. Also, I am keeping it here as well. Okay, so it will take some time. Remember. Okay, so meanwhile, let me conclude.
I have error on the second one code.
Okay.
I have error on the second one.
So now you see over the number of the epoch, as you can see, as the epochs are increasing, same phenomena you can see, the training loss is reducing and the test accuracy and the training accuracy is also increasing. So as it is almost 6, so I am just wrapping up the session. We are done with the hands-on part. So VGGNet, what we have seen so far, VGG11 construct a network using reusable convolutional block, but we have seen the different VGG model which can be defined by the differences of the number of the convolutional layers along with the output channel in each block. And we also have seen the use of the VGG blocks leads to the very compact representation of the network definitions, and it helps us to allow the designing of the more efficient complex networks. And in the VGG paper, we have seen the Simoyan and the Giserman also experiment with the different architectures. So we have given you a small demonstration of that type of the architecture, how to play around with the architecture and that kind of the thing. Okay, so let me also reshare the
in
other.
the third one, I have getting an error there, sir.
Which one?
Sir, third one, that is communicational part. The third one, that is I have error there. This I have sending them on your message on there. This side name NN is not defined.
Just a second. Let me check. Where you have posted it here?
Sir, this one.
So first portion, have you executed this part? First part.
Yes, first one.
NN, yes, first cell, because you see, otherwise it will not be able to execute.
Yes, I have executed that. The first one also, second one also. That the third one getting an error there.
I saw that NN is not defined. It is saying, okay, because it has not read the first one properly. That's why it is saying. Just rerun it. Let me post it. Because everybody has been able to reproduce it successfully. In your case, might be there is some mistake. You might have skipped 1 or 2 lines. Just cross-check it.
Yeah,
Let's cross-check it one more time. Okay, it will be easier for you. Okay, this is the first part. Okay.
Yes.
Okay. And the second part will be this one, defining the conv architecture. This is the second part. Okay. And the third part will be this one. Okay, this is the third part. And those who are getting the runtime error, I repeat, please close the other activities. Okay. So that you can do, you can simply go to the runtime, top of the bar, and manage session. Click on the manage session. For them, I'm showing it again. Those who are facing this type of the error, so just go there. Like for example, demo window, this type of the demo window. Okay, so here you go to runtime and click on the manage session. Go to runtime, click on the manage session. So here you can stop. If some other session is running, you can click on this cross button and you can stop it, which will show you the terminating of the other sessions. Okay, so in this way you can do it. Okay. So any more doubt or query? Because already the session time is over. So you can reach out to me. Okay, most welcome, madam. So you can reach out to me in my email ID if you face any difficulty later on. Okay, so I will post this notebook to you. sabyasachi@kgpn.iitkgp.ac.in. Okay, this is my email ID. You can email me anytime. Okay, and the other resources which I already posted earlier, I am resharing it. So if you need some guidances, so theoretical as well as the hands-on session talks are also available in my YouTube channel. You can directly access it from there. You can subscribe my YouTube channel and access it from there. And the career-related guidance are also given there in the Medium articles. Okay. This is also I have posted here. Okay. So thank you so much. Good to see that most of you have been actively participated in this hands-on session. Thanks to the respected professors, those who have participated in this FDP program and attended my session so actively. Thanks to the research scholars also. So it's my pleasure. I am thankful to the organizer again for inviting me for this guest lecture and hands-on session. Thank you very much for organizing this type of the impactful faculty development program so that everybody can get benefited out of it. Thank you very much. Thanks again. Thanks a lot. Thanks for your precious feedback. I can see you have enjoyed the session. Thank you. So any formalities left from my side, or otherwise I can leave the session, I think, as the session is over. Abhishek sir, your voice is not coming. Some noise, jittering noise is coming up. I think some network issue is going on there. So thank you so much. Thanks for your precious feedback. Thank you. Thank you. Abhishek sir, you are not audible. I think some network issue is happening. Okay, thank you so much. Thanks a lot. Huh? So I'm leaving the sessions. I will email the notebook to Abhishek sir. You will get it from there. Okay, thanks a lot. Thank you so much.
कहाँ तक पहुँचे हो? कहाँ तक पहुँचे?
Ma'am, may we start the session?
Yes, sure, we can start.
Hello everyone, I am Dia Agarwal going to host this session. It is my great pleasure to welcome you to the Faculty Development Program on the Deep Learning Applications. I take this opportunity to welcome our FDP speaker, Dr. Jagriti Seni. Today, ma'am will explain about gradient descent, learning rate schedules, and optimizers. We are privileged to have her with us today to share her knowledge and insights. Please join me in welcoming Dr. Jagriti Seni.
Thank you very much. So, good evening, everyone. We are here for one more session that will be on optimizers and gradient descent. And this is the last session from my side in this FTP as well. So, just trying to discuss few more interesting concepts with all of you so that you can just proceed successfully with your deep learning based projects. So I'm starting with a few theoretical discussions on the topic first, and then definitely we'll move on to the implementation part. So the topic for the day is your gradient descent, learning rate schedules and optimizers. The very first thing we are going to observe here is about gradient descents. And in order to understand the fundamentals of gradient descent, this is basically an iterative optimization algorithm that you would even learn when we are just beginning with some ANN based practice. This is the first most optimization algorithm that anyone would read when beginning with the ANN based models. The idea behind this is to optimize the cost function that can be to minimum value or towards maximum value. How we state this is like whatever you have considered as your cost function, because that may be different based on your model building. Like when you are working on classification, your more concern will be to enhance accuracy. That may be an increasing parameter. When we are working on regression parameters or regression models, then we work on error margins over there. So depending upon whether you have to reduce something or increase something, because some values are close to 0 are good, some values close to 1 are good. So accordingly, basically optimization functions or algorithms try to bring you the best optimal value from the cost function. That could be minimum or maximum. However, in most of the conditions, we use them for minimization works. If you have to use it for the maximization, some parameters you may have to tweak inside algorithm and it works fine for the maximization as well. Because majority of time you consider loss function in case of your accuracy parameters also. So accuracy you consider as a metric and loss function you consider as your minimization parameter that we can pass through your optimizer. These algorithms basically try to make few small updates into the parameters of your algorithm so that you can achieve the best value of your cost function or whatever parameter you are trying to focus upon while building your model. In the process of gradient descent, we generally start with some initial guesses. We always have an initial guess. This is the same thing that I discussed with you in the previous sessions also, like weights of a model we discussed about. We always start with some random set of weights to begin with a iteration process. So we always start with some initial guesses that we also call random values of your weights. And then the algorithm iteratively keeps on updating the relevant parameters with every next step or iteration so that it could reach to the cost function value, the minimum possible cost function value. Like you can see here, after every iteration, it is trying to update certain parameters to reach to the minimum possible value inside your convergence process. So while working on this gradient descents, we Preferably consider your problem domain something like a hilly landscape. And the idea is to reach to the minima right here. And the cost function basically represented as a surface plot over there. This is the generalization of the problem of the minimization with your gradient descents. So what we have to initialize here, one is your cost function that you are trying to minimize. Other is the weight parameter that we are going to update with reference to the minimization of your cost function. So that we are planning here, we are updating in your graph. At the same time, your gradient descent considers the surface like a hilly landscape, and we generally start from certain random value, like maybe from here or maybe from here somewhere. We just place a random value, and then this represents your initial weight basically. Then we apply a incremental step based on certain parameters out there, and we keep on reducing or we keep on minimizing your cost function with every next iteration to achieve the minimal possible value. So the idea is to take some small steps in the direction of steepest descent that we call right here. The idea is to achieve local minimum point, but there are different considerations with this also. For instance, when we are working on real data sets and we are trying to minimize something, there are different saddle points, different minima points that you will find on the surface. Like for instance, you can see in this image, there is one local minima point and there is one global minima point. This global minima point is generally the target that we have to achieve. This is the minimum possible value that your algorithm can achieve while minimizing your cost function. But sometimes what happens, your algorithm gets stuck with the local minima somewhere else and it doesn't reach to the desired position. And these things call some false terminations of your algorithm, and we are not able to recover from there so easily. In order to deal with this, there are so many hyperparameter tunings that you may have to do. You may have to rerun your models, you may have to test it with different conditions just to avoid your local minima. And more than that, it is more essential to initialize your initial parameters very carefully, because if you initialize some values randomly, like maybe they are far distant from the required positions, then they may again cause the local minima problem. And this local minima several times leads to very bad models because we are not able to achieve the actual minimal value required from the model itself. So while working on this gradient descents, we are generally not limited to linear regressions or functions that have just two parameters. Rather, they are complex functions that include several different parameters that we will also see in some coding paths also. There are plenty of different parameters that you may have to update with every iteration, and we just try to build a sequence of updates iteration after iteration to achieve the best possible value, because the goal is to minimize the cost function by adjusting all the relevant parameters inside your algorithm. While implementing your gradient descent, there are so many mathematical formulas that you will find in literature, in different research papers. I have included here some of the most basic formulas that you may need, which include your updation for weight term as well as bias term. You might have heard about these weights and biases while working on the basic neural network functions also. So I'm just including the basic parameters over here. However, depending upon the advancements in your algorithm and the requirements of your dataset, you can use advanced mathematical functions also for this. So what we have is, we just are trying to update the current weights and current bias values for the model. And for that, we take reference from the previous weight and bias values. And during the first iteration, these previous weight and bias values basically come from some random initializations. And after that, after first iteration, we start calculating them by using this formula. The idea here is to ensure that your W and B values are implemented and updated in every iteration at the same time, so that we can maintain a balance between the derivatives out here, and whenever we make a shift in the coming iteration, both these parameters are included in those step shift or direction shift anywhere. We'll just ensure that both of them play their role simultaneously. There are several different types of gradient descents that you may work around while building your models. One of the most basic we have is batch gradient descent. This is also widely known as vanilla gradient descent parameter or technique that basically computes gradient value for the entire dataset in every iteration. So here you can clearly imagine that you generally have, when you have a very big data set, it will automatically lead to computational complexity. You will have plenty of, someone is raising hand also. If you have any query, please let me know. You can post in the chat box also. If it is by mistake, then I'll continue further. So we are just trying to compute the gradients by making use of some parameters that are initialized while building your model. But the idea behind batch gradient descent is considering entire training dataset in every iteration. So definitely we may have to update several parameters on the entire data set, and it gets computationally expensive on the larger data set, and automatically leads to slower conversions for the noisy and redundant data set. So like if your data set has more outliers or noise, then definitely it will be deviated due to the influence of those outliers or noise. Will find it difficult to reach to the local minima in that case, because entire batch is being included in every iteration right there. The other alternative that we have in the list is stochastic gradient descent technique, in which we prefer updating parameters for a set of values or some subset of values in each iteration. The idea is to work on some randomly selected training samples at a time, so that we can have a faster response in comparison to batch gradient descent. So instead of picking up entire training data set in every iteration, it will rather work on batches of data. So there will be random batches of data on which it will be doing its analysis for reducing that cost function. The benefit of this is that it can adapt to the changing patterns in data very fast, because it works on all varieties of batches of data instead of being stuck with the global outliers over there. And it can also exhibit more oscillations, as you can see here, or due to these oscillations, sometimes it may take more time to converge. So there are again some advantages also and disadvantages also. Although it will learn better with the changing patterns of data, but because oscillations are more, so convergence time also may be different in comparison to the previous method. Some researchers have also introduced one more technique, that is mini batch gradient descent, which is basically a combination of previous two methods that includes batch gradient descent and stochastic gradient descent. So in this case, the gradient works on small data sets that we call mini batches of the training data set, and it combines the abilities of both your stochastic as well as batch gradient descent. The idea here is to create a balance between stability and computational efficiency of your model. And this is done by introducing some variety in your training process, where we update these batches. You can see like some random sets are being updated from your training samples to achieve. So instead of having so much of variation like we had in your stochastic gradient descent, the technique here in comparison to this that we were having with the longer convolution due to more number of oscillations, that is reduced here due to that proper segregation of batches of your data while ensuring that the outliers are taken away and to get more accurate results as well. So these are some essential techniques that are included in the gradient descents. However, in literature, you will find many other techniques also because several researchers are working in this area and they keep on providing new set of parameters as well as algorithm updates to work around this. Now, then we come to one important element of your gradient descent algorithms, that is learning rate. So we usually say that I can see that few people are raising hands time and again. If we have anything to discuss, please let me know.
Yes, sir. I have a question, ma'am. I have actually a question regarding that gradient descents. What issues can occur if we have large learning rate in the gradient descents?
Sir, we are coming to that part. I just started with the learning rate.
Okay, ma'am.
Yes, we are just going to discuss it further. So now we are coming to the learning rate importance and its different levels that we can have inside gradient descent algorithms. So what we have here basically, first of all, this learning rate that is generally denoted by alpha, or sometimes we also call it LR parameter. It helps you to ensure quick conversions of your algorithm for minimization of cost function, and it also plays an important role in controlling step size for your gradient descent process. But how all these things are going to work, that we need to understand, because there may be different values of learning rate. The first case we can have is like when learning rate is too small. What may happen in that case when the value is very small? Generally, we put this value of learning rate between 0 to 0.9, or these are the some common values that we prefer. 0.7 is the most commonly used value, 0.9 is another commonly used value, but we cannot say that this will work on all the data sets. We keep on changing depending upon the type or variety that we have in the data set. So what they say that when learning rate is too small, in that case, what happens, your algorithm is going to take very tiny steps towards the minimization of cost function that you can see right here. It is going to take very small steps because the element we have added is very small. So whenever a weight shift will be there, a small value will be added or subtracted from there. How weight changes happen every time, that we have seen with the formula behind. So there is a omega minus dw by dt factors that we add for omega as well as base. So the change value or the learning rate value, when that is very small, the addition or subtraction that we are going to do in the initial weight is also going to be very small. So the direction of change as well as the step for that change is going to be very small. And again, your algorithm is going to be very slow. It is going to take so much time to reach your ultimate goal. So maybe the task that you could otherwise achieve in 100 iteration, it may take like 1000 iteration to achieve the same task. So that will again put more burden on your processor, on your memory, because you are running so many iterations without a need of doing that by just initializing a small learning rate. Similarly, there is another case when your learning rate is too large. That is again a problem. If you have a very huge value of learning rate, in that case, the gradient descent can overshoot from your minimum values. For instance, if it started from here, maybe it will have a very large step that instead of moving towards this value, it will move towards this value. Again, if you are shooting it by a very huge amount, so instead of going downwards, it will go upward and you will have a great error margin again. It means instead of reducing the error margin, you may sometime even end increasing error margin by the end of your training. So in this case, again, we have to be very careful. You will find it difficult to reach the optimal solution. Sometimes your algorithm may even step outside the boundary values because of this high learning rate. So it will jump outside the boundary value and you will be left with the lost values. You will not have the exact convergence from your model behavior. So both these conditions are very bad. We generally need to optimize or find a very right learning rate, and again, that is definitely a difficult process. We cannot always say that this value is perfect for every data set. That is never possible, depending upon how in-depth model you have created in deep learning, how much training data you have, and what is the quality of your training data, what type of variance you have in your data. All these parameters are going to affect this thing. But still, there are some techniques that experts have invented to find right learning rate so that your this cost function reach to the minimum point swiftly without getting stuck in local minima or without getting overshooted outside the boundaries of your cost function. So one technique that is more commonly used by everyone, that is experimentation, definitely. The trial and error process that most of the time people use. We start with some reasonable initial value. We either start from the lower value, we either start from the higher value, and then we see behavior of the algorithm. Then we slowly try to change in your learning rate. Either we try to reduce value or increase value, whatever are the possibilities within your initial defined value, and we'll see if your algorithm starts converging somewhere or it starts overshooting. If the error rates increase after shift in your learning rate, then you try opposite value, means reduce value if you are earlier increasing it. So those things you can try. And when you iterate with multiple combinations over there with trial and error, you may automatically find the right balance. But definitely this is again a time consuming process because you have several values ranging between 0 to 0.9 also. So you may have to switch between them. Even some decimal point values may make difference. So you just have to be careful what trial and error process is giving you, and you have to observe its changes in the algorithm, and then you have to change the initial values again. Second technique, learning rate schedules also we can fit in. So instead of using a fixed learning rate for the entire dataset process, sometimes researchers plan to employ some learning rate schedules. And in this case, what we do is we keep on decreasing learning rate over time. Like we start from a higher value, and then over time, like maybe after every iteration, or maybe after 5 iteration, or maybe after 10 iterations, we try to lower down the learning rate. So it is like, you can consider it something like a simple for loop, like first run for 10 iterations, then reduce learning rate by this value. Run for next 10 iteration, then reduce learning rate value by this. So that kind of adjustments also we can do to ensure that your model has fast convergence. And along with this, definitely we can put up a patience parameter as well that we have discussed in the previous session also. So whenever your model finds accurate learning rate and it stabilizes its performance, that we can see with the patience parameter, so it will automatically give you the best outcome based on that. So either you can just finalize your learning rate with that previous random hit and trials, or you can use schedules. And schedules definitely are more appropriate solution when you have a very big batch of data again, and you have designed a very big model that requires a number of iterations to get optimized. So automatically it should get the learning rate updates inside. We can also have adaptive learning rates. That is another technique we can have, and that we can do with the help of optimization algorithms that are something like AdaGrad we have, RMSCrop we have, Adam we have. They help you to adapt learning rates automatically during the training process. And that we can do based on different parameters that we pass inside these optimization algorithms as well. Within Keras interface itself, there are 7-8 different optimizers that you will find easily, and you can deploy them within your model as per your requirement. During our previous implementations also, we have employed, I think, Adam optimizer we have used time and again. So I told you that we'll be discussing it further in detail. So here we are going to talk about that. The main idea behind this is to create a balance between different parameters of your model while balancing the learning rate in such a manner that we achieve local minima, the proper minimal value or optimal value within least possible time. So now there are plenty of optimizers that I told you already. After each iteration, the idea is to compare your actual data with the predicted data from your model and try to evaluate the loss function to calculate error, so that the weight updates we can plan accordingly. But now one question that we all can have is that how do we know how to update that weight after every iteration, or maybe after multiple iterations, to increase accuracy of the model? So this thing we do with the help of optimizers. So that weight change phenomenon, that is one of the crucial factor in your neural network based models, whether ANN, CNN, any of them. This optimizer plays an important role over there. So what it does basically, in case of an optimization problem, as we discussed so far, there is a loss function that we are trying to optimize, and we just have to arrive to the ideal weights to achieve the minimum value of that loss function. And the process that is used to do all this thing is called optimization, and the method that we use to do this is optimizer. So this, in order to achieve this optimization process right here, within gradient descent itself, there are although gradient descent is a widely used method, but there are many other optimizers also that we can apply for this purpose. The idea is to achieve that minima value on the surface that we have discussed already. So the role of these optimizers in gradient descent also is very important. Like, it helps you to calculate the minor changes in each weight parameter that may affect your loss function somehow. It may even help you to tune your initial weights for the gradient descent. So that initialization process also we can manage with the help of optimizers. But sometimes there are some complications within the algorithm itself that restrict it from measuring the change in the parameters. So in these cases, we apply additional optimizers that we are just trying to discuss right here. So those parameters, those additional optimizers will help you to understand whether, while updating your weight value, whether you have to subtract it from like certain value or add certain value, and what is that value exactly to achieve the minimum loss function. So this is the entire story that we are trying to cover with the help of the optimizers. This local minima and global minima issue that I have already discussed, these are associated again to your these Keras optimizers also. And these are more important when we are talking about a large multidimensional data set where there are more chances of getting multiple local minimas. So you can consider it something like you are throwing some balls from here, like for instance. So you never know whether the ball will be stuck here or it will go this side. So the same process happens in case of your optimization process as well. Maybe our algorithm starts from some peak values like here or here, then we try to reduce. So we never know whether your model will be stuck at this position or it will be able to achieve this lowest minimum possible position. So that only we are trying to minimize with the help of your optimizers. So the very first optimizer that we have in the list is your AdaGrad optimizer. The process behind this is very simple. What it does basically, it works very carefully on every individual feature on your data set. That completely means that some of the weights in your data sets may have different learning rate than others. So whenever we deploy a CNN or ANN based model, there are always some weights that are going to treat different features in different manner. And with this AdaGrad, what we try to do basically is we try to apply different learning rate possibilities to all the initialized weights. So instead of increasing or reducing weight value by a specific number every time, chances are that we may have different updates to different weight values in every iteration. This type of optimizer has a very good performance on sparse dataset, where either you have so many missing values or so many zeros in your dataset. So on that kind of datasets, this optimizer work really well, because it will not get stuck with the sparsity of the dataset, since we are applying unique learning rates to all the weights. So even if some weights are assigned to the zero values or the missing slots, they will be updated accordingly based on what data they are getting from the outside. Moreover, in this undergrad optimizer, there are frequent updates into the learning rate during the entire training process, and there are multiple parameters that we are going to pass into this. For instance, when we are initializing it with the Python process, you will see that these are the essential parameters that we are going to pass inside. It includes the learning rate parameter that is essentially added. So this is a default value that we are seeing here. We can change these values definitely. Then you have the initial accumulator value that is by default 0.1. You can change this value also. And what is the role of this value? Basically, this is the starting value for the parameter. So whatever momentum you are initializing for your model, that initial value in the form of a floating point number we are providing here. Then we have the epsilon value with a default value of this. This is again a small value that is used to sustain the numerical stability within your model. So this is again a floating point value that we provide, and then the name of the parameter we add here. And after this, the keyword arguments we try to initialize over, so that your algorithm or the function takes all the keyword arguments that we are supplying from the outside with the relevant values of it. So this one we just put up as a additional parameter into the model itself. With this undergrad optimizer, although it is best suited for the sparse dataset and it updates its learning rate with every iteration, but still there are some disadvantages. One is that the learning rate becomes small when an increase in the depth of the neural network occurs over there. Because since we are changing learning rate in every iteration, so this gets a complicated task when we have a very in-depth neural network. And sometimes it may even lead to a dead neuron problem, because this particular system we are deploying on a sparse dataset also. So if there are like more missing values and zeros, chances are that there will be several dead neurons that are getting nothing from the outside, and they are just complicating your network structure by adding some unwanted computational complexity over there. Then we get one more interesting option among optimizers, that is your RMS prop optimizer. This is one exclusive version of the undergrad itself. Means this is like a enhancement in your undergrad itself. And RMS prop here is root mean square propagation, basically. That is the full form of this particular. And it was developed by Jeffrey Hinton recently. And instead of letting all the gradients accumulate for a single momentum value that we provide, it only accumulates gradients in a specific fixed window that we supply during the parameter updates. So it can consider various updates in the individual parameter in reference to the momentum value that we have supplied. So in the previous one, if you check, there was no momentum value. Initially, we have not provided any momentum value. But here there is a momentum value, although it is listed 0.0 here by default. But we can update this value as per our requirement, and then we can see the changes in the outcome over there. So other parameters are almost similar. We have the learning rate parameter, we have epsilon, and we have the name and keyword argument information over here. Other than this, you have RHO parameter that is by default 0.9. This is basically a discounting factor for gradients. So whenever we are updating gradients, the discounting factor is very important over there to ensure that we are getting accurate updates after each one of the iterations. Then the momentum value also we are passing inside. This helps you to ensure adequate direction for the movement of your step size. Like we have seen here in your these changes that we have on the surface. So whether your reduction has to be in this direction or in this direction or in this direction, that decision is very accurate in case of your RMS prop. So it can handle your surfaces very accurately. Then there is one more that we call centered, that is by default false, but this basically helps you to train your model even if it is computationally expensive. If you set this value true, it will ensure better normalization of the variance in your data set. So proper centralization for your all the high end values within the data set, that will be done very precisely with this additional parameter. By default it is false, but we can make it true as well. Then we have some advantages and disadvantages of this RMS prop optimizer. Now learning rate in this case is automatically adjusted. Secondly, we have discrete learning rate for every parameter again, because again this is just an enhancement of the previous one, so the same pattern it is following. It offers fast convergence due to the frequent updates that we are having, but this is again less stable as it may oscillate around optimal solution, because we are making updates very frequently over here, and at the same time momentum related updates are also there. So directions may be sometime into wrong side and it may oscillate so much before reaching the optimal solution. Also, it requires a large number of hyperparameters. So accordingly, the regularization parameter we may have to update into your CNN model, or number of iterations also we may have to increase to work around those higher number of hyperparameters. And again, it is sensitive to feature scaling as well. Why? Because based on the previous information that we are getting from the other AdaGrad, it works on the feature specific parameter. And for every feature that we are adding into the model, again, the momentum values are going to be different. Your learning rate values are going to be different. So definitely it may sometimes get more sensitive to the feature scaling. Then we have ADA Delta, one more extension to the AdaGrad itself. And this is basically adaptive delta. That is the full form of this one. In this particular algorithm, we have delta value, that is basically the difference between the current weight and the newly updated weight. So whenever we are just updating the weight values, it will take a reference from the continuous changes that are happening in the weights. The recent weight, the current weight, or the previous weight values, it will every time calculate the difference between them, and it will try to just bring out them to the optimal value to reaching your minimum possible cost function value. This ADA delta is considered to be a more robust extension of your AdaGrad in comparison to RMS prop also, because here the learning rate is based on the moving window instead of just being relied on the feature scaling or being relied on the feature changes or the sparse data set only. Here we apply a moving window also into the system, so that it can just observe all the past gradients in the system. It can observe their pattern, and based on that it can decide its next step for the reduction process. So while building this kind of model, again, we have some basic parameters to be passed. That includes your learning rate, RHO, which is your decay rate, and that epsilon value, as we discussed already. In case of ADA delta, it is not always essential to set initial learning rate. However, in case of your Keras optimizer initialization, we pass learning rate value to this. But otherwise, if you don't even initialize, it will automatically take a random value by considering the past consequences in your dataset. And it is generally computationally more expensive. Why? Because it is every time making calculation over the change in weight values based on the window size. So depending upon how big window we have passed into this by updating the parameters of the model, it will make several calculations in every iteration. Then we have Adam optimizer. This is adaptive moment estimation optimizer basically, and it is always calculating the current gradients in comparison to the past gradients, almost same as the previous model. But in this case, we also utilize the moment of the concept of momentum. In this case, in ADA delta case, that momentum concept was again missing. But in case of Adam, we again add that momentum effect, but with the two upper and lower values over there, beta 1 and beta 2 values we pass this time. And what it will try to do, basically, the beta 1 value is basically your decay rate for the first moment. We describe it in the form of a constant float value every time. And then beta 2 is the decay rate for the second moment. So whenever in every iteration we are making any direction change, it will calculate the direction change between the beta 1 and beta 2 value, and that will sometimes restrict your model performance based on its projections toward the minima values in the surface. So one disadvantage that we have seen in the previous model where momentum term was included, we have seen that it may sometimes take so much time because of the oscillations. It may take so much time to optimize over there. But in case of Adam, the implementation is easy, the computation part is reduced, and it requires very less memory. However, there may be a weight decay problem in this case, because every time the beta value we are getting stuck with, and it will sometimes create a weight decay problem, and sometimes it may also not converge. So that issue may happen with several optimizer, that convergence is not always guaranteed. They just try to bring out the best value that is possible, but sometimes when the data set is not suitable as per the requirement of certain optimizers, so they may even fail. But however, still they are good enough. At least one of them will definitely fit into the variety of data that you have. So we sometimes have to do hit and trials, that which one of the optimizer is best suited for your kind of problem. We cannot always say that only one will work with all set of data sets and models out there. Then we have one more, that is ADAMAX optimizer. This is an alteration in the Adam optimizer itself, and in this case what we do is, it is basically built on the low order momentum, that is based on the same values beta 1 and beta 2 although, but in this case the learning rate is changed every time based on the characteristics of data. So this is more dependent on the behavior of your data. Although it will increase the learning time, or it may also increase your optimization time in the model, but still, because it understands the behavior of data, so sometimes that is a useful feature for depending upon what kind of model we are trying to build. And it is more preferred in case of your speech data processing, because in speech data there may be several noisy conditions, some change in pitches also is more frequent over there. So in order to understand those patterns, those changing characteristics of data, this ADAMAX optimizer is more preferred in case of speech data processing. Few advantages of this is that it helps to make your algorithm more stable, that we have seen, because it is going to help you to adjust learning rate based on the dataset characteristics out there. And it also requires lesser tuning for the hyperparameters, but some generalization issues are there. Although it goes well with the speech dataset, but with other types of dataset, sometimes it faces generalization issues are there. One more we have is Nadam optimizer. This is basically a combination of Nestrov and Adam optimizer. A combination of both these we apply over here. This was developed in 2015 when it was first brought into the notice by a research paper out there. And in this particular method, we follow the traditional moment optimization based on the Nestrov escalated gradient function. The idea is to update the gradient values, or we can say the weight values, every time by considering the previous update vector sequence. So instead of considering the single value from the past set, it will create a vector sequence from all the past weight changes, and it will observe what kind of changes we are following. We are adding something or we are reducing something, and it will every time consider whether we are moving towards the loss parameters in the surface, or whether we are into some saddle points, or we are into minima, local minima, or we are moving towards global minima. It will every time do that calculation with the enhanced algorithm that we have provided inside. So instead of adding into some suboptimal or false direction, it will always try to find the optimal location for the momentum change as well as for the dropping down the loss function value. So that it follows with the beta 1, beta 2 as well, and the learning rate parameter. All these three parameters are going to be helpful in the processing of this optimizer. So advantages of this is it ensures better results for gradients due to its high curvature and noise handling ability. It learns faster. However, may not converge sometime because this again is proficient in some kind of data sets. Although it provides good speed, it is a responsive one. Has enhanced stability as well. But sometime with very complex data sets, again this optimizer may also fail. So again the same issue, that experimental process is always required, that which one of the optimizer will fit for a specific type of data set. Then we come to one of the most popularly used optimizer out there, that is your SGD optimizer. This is one of the most commonly used. Adam and SGD are the commonly used ones. So this is basically stochastic gradient descent that we have discussed as a basic optimizer in the beginning also. In this case, it will always perform some redundant computations on the bigger data set. It will keep on recomputing all the gradient values out there before making any of the parameter update. So although it is computationally very expensive, but still it is preferred in several cases because it ensures frequent updates in the values, as well as it deals with the variance as well as your fluctuations or noise values in the data very precisely. The elements here include learning rate, momentum. The Nestrov, this function is by default false, but we can change it. We can make it true as well, so that if the Nestrov momentum has to be updated in the system, that will be made true. So in that case, it will take some effect of your Nadam optimizer as well, and it will to perform the dual operation. This particular algorithm requires lesser memory space, the frequent alteration it offers to the model parameter, which leads to better optimization with the reduced noise effect on the momentum as well. So there are few disadvantages also. Computationally expensive, that I already discussed, and it also leads to high variance sometimes due to the frequent changes that we see inside your model parameter updates. So this was all on the theoretical side that we have seen for different types of gradient descent algorithm, the learning rate issues, as well as for the optimizers out there. Now we are switching to a small implementation based on all these discussions that we have done. And I'm not going ahead with a very complicated one. Rather, I'll be following one simple method right here. We have already trained MNIST dataset on the first implementation session that we did on the second day with the deep learning. So today I'm using the same dataset, but instead of just running a basic model only, I'll be using a combination of optimizers. All these optimizers I'll add into the system, and we'll just try to compare what is the difference in the outcome based on the different optimizers out there. So the idea is to compare performance of your model based on selection of different optimizers. So this will just help you to get an idea about how we implement these optimizers in the system, as well as what change in the accuracy we can see with reference to different optimizers. So before I start implementing, those who are going to do it for the first time, or those who are dealing with optimizers for the first time, we have them from the Keras repository directly. I have opened up one Keras repository here for you. So this is a long list of optimizers available. Few of them we have discussed that are more popular. Remaining ones also you will find right here. This is the entire list of optimizers we have within Keras. So the most popular ones include your RMS prop, SGD and Adam. Remaining ones are some advancements of these basic parameters or the basic optimizers, and we have made some algorithm or parameter change into the initial ones to get these new ones that we have discussed so far. So let us start implementation, and for this, first of all, we'll just load some libraries over here. We'll just import necessary libraries. All of you can start doing all the processes side by side. I'll be sharing code in the snipper window. So we know the libraries that we need for the process because every day we have used this library. One I'm getting is TensorFlow, and along with the TensorFlow, I'll be importing Keras from this particular interface. Then I'll go again to the TensorFlow.keras, and from here I'll import some layers to build my model later on. Then I'll again go to TensorFlow.keras, and today I'm adding one more thing over here, that is callbacks. One more concept I'm introducing here. Sometimes we add callbacks to the model, and these callbacks generally include two things. One is model checkpoints that we can add, and second is early stopping condition that we add with the specific patient's parameters that we have discussed in the previous sessions also. So model checkpoint will help you to store the performance of your model at a centralized place within your system. So we can just create a sample folder within your system where all the checkpoints of your model performance iteration after iteration will be saved. And early stopping function basically helps you to decide at what value you want your algorithm to stop, even if it doesn't have to perform all the iterations. So what will be the minimum value that you will accept before stopping your model? So both these conditions we are going to use further to build your model. Other than this, I'm going to get my matplotlib.pyplot if required in between for some kind of plotting. Otherwise, we can just drop this as well. Pandas as PD may or may not be required, but just importing all the basic libraries right now. NumPy as NP also have imported. So all the basic libraries and TensorFlow modules I have imported right here. So I'm just running this, and if it works fine, I'll be sharing it with all of you. In the meanwhile, I'll just put up the next task that we need to do. That is to load your MNIST dataset. I'll just get the digit dataset that we have used earlier as well. I'm putting this code inside your snipper window for all those who are doing it side by side. And also in the chat window, I'll update it. Let me know when you all are done with this. Mine is still running, so this may get done within few seconds. All of you can let me know when you are done with the library process. So I'm getting one typo over here. Let me check. Model checkpoints. Okay, there is one typo. We may have to correct it. This has to be point with small p. I'll correct it in the snipper code as well. Now this is working fine. So this one only I'll update right here. This should be fine now. If anyone is getting error with the previous one, I have just updated the new one in the snipper window, and I'll post this entire one in the chat window as well. So after this, we are just going to get our data set. So we'll just store it inside MNIST variable, keras datasets.mnist I'll do here. And we get multiple elements out of this particular data box. So same I'll do here with xtest and ytest parameters. Outside this, I'll pass mnist load underscore data with empty brackets so that I get everything out of this folder. I'll run this, and you can check even the shape of this data that you know already. You can pass the shape function for that. Currently, I'm just loading my data set over here, and I'm putting the code within the snipper window. All of you, let me know when you are ready with the data set. If anyone has any query, please let me know. You can even post in the chat box. I can look after over there.
Good evening, ma'am.
Yes, please.
Ma'am, actually, the first code I have gotten an error there. That
What
is,
error you have, sir?
that is I have sent on the chat box also. Can check
Okay,
now.
let me check.
This one is one, yes.
This one? Sir,
Yes.
I have just explained this error and I have corrected this code in the snipper window also. Maybe you have not heard that part. We have just changed this points to small p and we removed s from there. There was a typo while doing this.
Okay, 1 minute. I check now.
Yes, you just need to check this one.
Okay, okay, yes, yes. Okay, thank you.
Okay. So those who don't have snipper URL, I'm just putting it right here. I'm using same snipper every day, so you can follow the same one. I have just created one new sheet over here to locate day 5 session. So here I'm posting everything. So I hope that most of you must be ready with the dataset now. If I need to wait for anyone in the meanwhile, please let me know. Otherwise, I'm just moving ahead with pre-processing of dataset. I'll do just a minor pre-processing. I'm not going ahead with a very in-depth pre-processing over here because we have already understood all these things. So only minor things I'm doing here. So xtrain, one variable I'll create, and xtest is the other variable that I'll get out of the process. On the xtrain, I'm passing reshape parameter and -1, 28 cross 28. Another way of normalization I'm using here. We in every case study, I have tried to show you a different way to normalize your data set. Divide by 255 logic, I have already shown you. We have discussed that. And this is just because of the scale that we have within your metrics. I have shown that you with the various data sets. The reshaping method, we are using different. This is basically the size of matrix that I want after reshaping. -1 we utilize for the last observation or for the last calculation that you have in your array. So I have shown this in the initial days also when we were talking about slicing operation. There was a meaning for the -1 over there. So the same technique we are following over here. Either you can pass the value that you know for the last element in your dataset, or you can pass -1 directly. So that will do the same thing. So for this one, I'm passing here the test, and remaining values I'll keep as it is. Let us run this part. This is working fine. And I'll put it here and in the chat box as well. Let me know when you are done with this. I'll wait for the responses in the chat box. Thank you very much, everyone. So now I'm building one basic CNN model. Again, I'm using one different approach here to build CNN model. This time I'm going to do this with the help of a function. The variety I'm adding every day just to ensure that you understand the fact that there are unlimited ways to do same thing in the coding. This is completely about how you want to proceed with, how friendly you are with the coding environment. Accordingly, you can use any technique. So I'm using here create model function within which I'm initializing keras.sequential model. I think this S should be capital, then we'll be able to initialize this. And then layers I'm passing. I'm not passing so many layers. The initial layers I'll take by default one. Only the end layers I'm passing over here, creating a very basic model with dense layer where I'm passing my ReLU parameter. Along with this, I'll put one more sequence of dense layer that will be on the output side with 10. We know that in this MNIST dataset, we have 10 classes, so same I'm passing. And on the output side, we always use softmax activation function. So that I have updated here. And as a part of your function, I'll write here return model, so that whenever I call this model, it will return me this created model that we have passed inside. Let me check if we have any typo. I can see some red lines over here. Yes, I need to pass a comma right here, then it will work fine. The separation between elements. So I'll just run this one. This looks fine. If there is some error, that we can see only when we call this particular function. But however, in the meanwhile, you can just run it so that it will be saved inside your memory. So we have just created one basic model, and I have not passed any optimizer into this model right now. So before I compile this model, what I'll do is I'll list multiple optimizers that I can use for comparison purpose. So I'll list multiple optimizers. What I'll do is I'll create a list sequence. So name I'm giving is optimizers, for instance, and then I'm creating a list sequence over here. All of you might be aware that this square bracket we use to create a list. Then I have the first one is from the optimizers sequence. You can see here I have shown you that this is the Keras optimizers sequence. So it falls within the optimizers. So those who need more reference at how we call, you will always find it on the official site. Like this is the way to call your optimizers. But currently I'm using a sequence of optimizers. So I'll just use this part first, and then one by one, all of these I'll pass into my sequence. So Keras optimizers. First, for example, I'm passing SGD. Keeping empty brackets means with default parameters. Later we'll try to change these also. So second optimizers I'll add is, for example, RMS prop. In this we need small p, RMS prop. Then third one I'll add is, for instance, we have studied about Adam also, so that also I'll pass here. Then another optimizer I'll add is other delta, for example. One more I'll pass with your other grad, that also we have discussed. Then we have, for instance, Nadam optimizer, that also we have discussed. And one more we left is with your Adamex, that also I'll pass. You can pass remainings also that we have in this list. You can pass any number of optimizers. We are just trying to see their performance in comparison basis. So these are the all elements or all optimizers that I want to pass inside this list. And you can see all of them I have used with empty brackets. That means I'm just using default parameters for each one of these. Later on, I'll show how you get the default parameter information also, although I have shown them in the slides also. But on this official page of optimizers also, you will find that information. So let me first run this, and then I'll proceed further. I'll call this list later on while compiling my model. All of you can just get this list ready on your system. Then I'll set compilation variables, which is one additional thing we are doing today, because I have called two variables in the beginning and I discussed both of them with all of you. So one was the checkpoint. So I'll just call that model checkpoint over here. And inside this, I'll pass the location where I want to save my model checkpoints, and in which file sequence. That will be an IPyNB file with checkpoints. And we always get it with Keras extension, otherwise it will fail. Sometimes we have H5 extension also. I'm using Keras extension because it works fine with the sequence that I'm going to follow right here. Then next thing I'm using is what your model has to monitor while storing these checkpoints. So that I'll be storing is accuracy. So we have to focus on accuracy while building up your model checkpoints. Verbose, I'm keeping 1. This we have discussed already. When I need to see iteration wise outcome of my model, I use verbose equal to 1. If you put it 0, you will not be able to see that performance. Second is early stopping condition. So that also as a function I have called in the beginning. Inside this also, I want to monitor accuracy parameter. I'll pass one more parameter inside, which is mode. What this parameter will do, basically mode min I have passed here. This helps you to monitor at what point your training or your this optimization process should stop decreasing. So whether we are focusing on max values or min values or some auto updates, that we are basically trying to define. So when you are working on a minimization problem, we apply this min automatically. If we are using max operator over here, then it will stop training when monitored quantity stops increasing. In this case, it will stop when the monitored quantity stop in decreasing. So whether we are working on decrease or increase, accordingly mode will pass. Then here also I'll pass verbose so that I get information about this in every iteration. Patience parameter also I'm passing right here. Patience parameter, this is required with the early stopping. So for how many iterations I'll wait for this reduction. So I'm saying that up to 5 parameters only, I'll ensure that there is a relevant decrease. And also by what value that decrease I'll accept. So min delta value I'm updating here 0.01. Means if there is no further change by min delta value up to 5 iteration, I would like to stop my this model training. So that sequence we have updated over here. Now everything I have created for my model sequence, and it should be ready for the training process. I'll just run this part also. If it is fine, it should get green tick. I'll update this right here for all of you as well. So after this, what we'll do is we'll try to train or compile your model. And inside this, I pass some parameters. One is I'm declaring a result section because I want to store results for all the optimizers. That I'll pass into this result parameter. So I've created a simple dictionary sequence over here. Empty dictionary basically I have declared for this results. Then for loop I'm designing to scroll through all my optimizers that I have declared on the top as a list. So it will just go through those optimizers list and find one optimizer at a time. And based on that selected optimizer, it will do some sequence. Like first, it will just call your create model function that I have created right here. This create model function, it will call first. Then what I'll do is I'll print just an empty sequence. This is just because I want to see clean outcome further. So empty sequence, then I'll print name of my optimizer that I have taken from the list. After this, I'll just try to compile this particular optimizer that I have just taken from the list. So I'll use compile over here. And inside optimizer, I'll pass optimizer parameter that I'm getting from here. So the same variable I'm passing. After this, the loss parameter I'm updating. We know that when we use this MNIST dataset earlier, we use sparse categorical entropy at that time also. You have other techniques also that we have discussed in different sessions, so you can try any of these. Currently, I'm using sparse categorical entropy for your loss function. And matrices, we already know since this is a classification kind of problem, so I'll use accuracy as my main metric over here. So this should be fine with your for loop. What we are doing, scrolling through all the optimizers, calling my create model function, printing an empty line, then printing name of the optimizer selected from this sequence, then compiling my model for that selected optimizer at once. And after this, I'll just get history of my model within this for loop itself. History is equal to model.fit. So we already used this history parameter, the same I'm using. This is basically to store all the performance variations of your model. X-train, Y-train I'm passing here. Epochs I'm passing, for instance, only 5 epochs I'll run. You can change it for the higher level also to see enhancement in your outcome. Validation data, I have not separated validation data earlier, you have seen. So I'll use only X data over here. Otherwise, the best recommendation is to separate your validation dataset already, then pass that validation dataset only here. So this is just because I'm only repeating things from the previous sessions. So I just believe that you all know the process, and later on you can do it with the accurate process as well. Callbacks, these I have initialized, so the same I'm just calling here so that they also get fitted into the model, and accordingly the checkpoints get saved and the early stopping condition also get applied on your fitting process. Then we will save the results sequence that I have declared as an empty dictionary over here. So what I'll pass inside this dictionary now, I'll create one optimizer class sequence. So class I have created, inside this I'll pass name that I'm getting from the for loop over there, and then history for that particular optimizer I'll be saving. So history. So a simple sequence I have created by following variety of techniques from Python sequence. And let me run this. If it works fine, I'll be sharing it with all of you. Yes, the epoch started. So all of you can start running it. In the meanwhile, it will take some time to run. Although I have not added so many epochs, so it will be like a faster one. Only 5 per algorithm we have. So first it is running for SGD. You can see first it is running for SGD because that is the first one in the sequence. So 4 out of 5 we are running right now. The accuracy you can see, the loss parameter you can see. The last epoch for the SGD optimizer, it has started. After this, it will switch to the next one. You can see RMS prop. And you can see this space here. This is why I added that one, this basically, so that I can see little bit of space when it switches to the next optimizer, just to get a cleaner outcome. We can do these kind of things, some presentable outcome when you need. So these spaces will help me to ensure that it is shifting to the next optimizer now. So let us see what we are getting in sequence. In the meanwhile, I'll put up one more code here so that once it finished running, we can plot these matrices. So let me discuss that part with all of you in the meanwhile. So what I'll do here is plot figure. Matplotlib I have already taken on the top. And here the figure size I'll pass is, for instance, 10,6. And then I'll pass for, because we have to run it for all the optimizers. So for optimizer name, comma, history in results dot items. This sequence that I have here, I have stored recently right here. The class name sequence I have stored here. So the same I'm calling from the results dictionary. And then I'll be creating the plot sequence with the history. Inside this, I'll pass my validation accuracy. For example, you can plot train accuracy also, that is your choice. But I'm updating right now is validation accuracy. And label I'll pass every time is name of the optimizer that we are getting in the loop sequence. So with reference to every optimizer, we are going to create a plot over here. Then outside this for loop, I'll add the global parameters. The first one is your epochs we'll add or as an X label. Then we'll have Y label. Inside this, I'll add validation accuracy because that is the thing we are trying to plot right here. Then we have plt dot title for the graph. So this one I'll write is optimizer comparison, for instance. Then next thing I'll try to plot is legend because this time we'll have multiple graphs on the same XY graph. So we'll just try to get legend also for that. It is still running, and after that we can run the plotting metric sequences. I hope this should be fine. So I'm sharing this in the snipper window. If we have any typo in this, we can correct that later also. So let us see where we have reached right now. Okay, this is on the ADA delta. So after this, it will go ahead with ADA grad, Adam we have, and Adam X we have. So we'll just wait for a while we get these results. You can observe that a few of these models are having very small accuracy. You can see for this ADA grad accuracy is 0.57 right now. The previous one we were having is with ADA delta. This was having again very small starting point. If we go up, this Adam was having a good starting point, 88%. Before that, your RMS was also having almost similar 88%. And before that, your SGD was having 73 as start point. However, it shows a great progress over epochs. 93 it could reach. And the second one even could reach up to 98. So we can see a great progress even within the 5 epochs that we are running. But completely depends on which optimizer is more suitable because not all of them will progress with the equal level in 5 epochs. You can see some are even in their 60s over here, and some of them are able to reach 98 or 97 also. So that is the basically difference that we have when we choose a different optimizer for a kind of training. This is why you always have to be careful which optimizer is more suitable for your kind of data and what in-depth model you are trying to build. Based on that only you choose your optimizer sequence. And currently we are even running it with the default parameters only. We have not even updated some additional parameters. Parameter values are default only. So first we'll just let it run and then we'll try to change little bit the parameter sequences by following it from here. Okay, in the meanwhile, when it is running, I'll show you the optimizer default parameters also. What you can do is just click on this, it will take you to a new window. And here you will find all the default parameters for each one of these windows. So let me just share this document with all of you so that you can observe it parallelly. See, when you need to know remaining parameters or essential hyperparameters that you can tune inside every optimizer, you will see that list over here. In the PPT, I have picked up just few of them that are more essential. However, there are many others also. So complete reference about each one of these parameters also you will find. See, they have described everything very well on the official website itself. That what is the meaning of each one of these parameters, what are their default values and how you need to use them. Everything you will find in detail. So even if you are a beginner and even after this session you want to implement it on any other data set, you can find some reference from the official website directly. Same you can do with the remaining ones such as RMS prop we have here. Again, a long set of parameters with their default values, the change values possible, numerical or categorical, whatever you have to pass inside that you can find here easily. So we can see your model training is done now, and I'll just run this plotting sequence over here. And this is what I get. You can see some of them are very bad at their conversions, and the maximum one we are getting with these three, green, orange, and a brown one. So we can see green is your Adam, orange is your RMS crop, and one is your Nadam also, that is also showing good progress. So we can see these three are almost close enough, remaining are slightly low. And if we can compare these values right here, you can see this is your sequence with Adamax. We are getting validation accuracy up to 96 we are able to get. If I just try to print these results separately, then also we can see them right here. So let me just print results right here. You can see for every optimizer, because we have created a dictionary sequence in the beginning, so accordingly it is saved. So for SGD, in the first epoch it started from 83, in the last it could reach up to 93. The loss also you can observe accordingly. For the validation, it started from 90 and it could reach to 93 by 5th epoch. RMS prop started from 92, it could reach to 98. So you can observe all those conditions here that we discussed in the theory also, that the starting point also matters, from where it is going to start. If it is starting with a good value, means if your initial parameters are good, then it can converge easily. However, if we compare with the other ones, like the below ones we have here, ADA delta, it started with very low value, and the convergence on the low number of epochs was also difficult. Maybe it could converge, but after maybe 50 epochs or maybe 100 epochs, that would be a good option for this. So it may take longer time in that case. Similarly, if we go ahead with the Adagrad, this started also with approximately good value, but it could reach only up to 89% over here. So Nidam started again with a good value, so it could reach even up to 98. So this looks like a good performance right now. So accordingly, all of them we can compare. It started with 90, reached up to 96. So this is a quick sequence we have seen for all the parameters right there. So we can just take a reference of these results initially. Then I'll try to change a little bit with the learning rate parameter, for instance. We have although several different values that we can pass inside. So I'll store this inside here so that we can compare it with the first iteration. And in the meanwhile, I'll update, for instance, all of you can try these things. For instance, here we have, for all of these, the learning rate parameters we have passed like the default ones. Maybe I would like to change this learning rate to some other value. So I'll pass here and I'll make it maybe a higher value, 0.7 for instance. I made it was 0.01 earlier. So for all of them, I'll just use this random change and we'll see how your outcome get influenced, whether it will be good or bad with this selection. So that we'll try to observe in the meanwhile. So I'll just run this one, and these ones one by one will just update. So let us see, we are running it again. We'll observe what changes we will see in comparison to other one. And you can even observe here, this time it started with accuracy of 85. Let us see how good this learning rate goes. Although we always prefer that your learning rate value low, if it is low, it is good because it will make computationally less expensive. Higher values always lead to more computational burden for the system. Lower values are always good. So sometimes what happens when we are training our model, you find your model good enough to converge on 2-3 different learning rate values. Some are low, some are high. For instance, when you observe, you find your model converging good on a learning rate of 0.01 also, and a learning rate of 0.5 also. So in that case, we always go with the lower one because that will be computationally less expensive if you are getting approximately same performance on both those learning rates. These are some common chances you will find, because when you are doing experimental work, you will observe these things. So we are just running it with the next sequence, and you will see that there is a very bad performance also we are getting from the RMS prop this time. The loss function is a very huge value right here because we used a random learning rate which is very high, which may not be suitable for this one. So you can see it started with a very huge value of loss. Earlier this RMS prop, if we compare, it started with, you can see 0.25, very small value. So these are the differences we get when we choose wrong parameter. Suddenly your this algorithm will shoot outside its boundaries. So although it tried to converge to a lower value, but still it was into more than your decimal frequency that we were getting earlier. So 2 is not, we cannot say that this is a minimal value we are getting. And even accuracy is very bad this time, 0.18. Earlier it was crossing your 96 or 97. So it failed very badly with this new learning rate. Same happened with the Adam also. You can see it failed also. Earlier it was a very good one. It was on the top rank. So this time it is very bad, performing very bad. So these are the differences we get with the change in your hyperparameters. How we are changing hyperparameters, that is going to be make a huge impact on your model performance. So we'll just have a quick graph plotting over here, that which one of the optimizers could digest this huge learning rate value. So that we'll just try to compare over here. It will just take a few seconds. ADA grad we are just running right now, and after this we'll see this graph. Currently we are able to see that your ADA delta is on the lowest one, and these we have seen as top performers. Let us see if the higher learning rate goes good with the ADA delta also. And it seems like it is going good with the ADA delta this time. You can see this is reaching 97. So even the higher learning rate went good with the ADA delta. It was not so good with the lower one. So that difference with all the optimizers may be there. You can even pass other parameters also that we have over here. But there is one thing I would like to suggest to the beginners. When you are making adjustments with the default parameters of any function, don't try to change multiple parameters in one go. We always try to create a balance between parameters, and we change one at a time. We observe its impact on the model performance, and then we apply other one. For instance, if you change like 2-3 parameters altogether and then you run your iteration, whether it goes bad or good, you will not be able to observe clearly that which one of these parameters added into influence of your good or bad performance. So always change one parameter at a time, see its impact on the performance of your model, then change other parameter, then look at its impact on the model, and then you can compare easily that which one is good and which one is bad to change or manipulate. Do this with all the parameters that you want to add into your model. This is the process of hypertuning, and that is why we say that it takes longer time to hypertune your models, because it is not like a random set you can pass anytime. You have to create a balance between all these parameters. For not all the data sets, these default values will be good. You may have to change them slightly based on how your data set is being processed by the model. So whenever you make a change, observe its impact. And it is not always necessary to pass all the parameters or only one parameter. That is completely your choice. How much create a balance in your model, and there will be 2 level balance. One is balance of your model performance parameters, means you need good accuracy and a very small loss value out there. Second is balance between these hyperparameters with each other, because sometimes what happens, you get good balance with the learning rate, but when you change momentum value, even it deviates the performance for the learning rate also. So what we are creating for a balance between these two, that will be again an experimental process, or you add some additional like adaptation algorithms in between, so that they adapt to each other, and then you get the final performance based on that. So our model also finished running here, and I'll just plot it again. Let us see which one is the winner now. So we can see your, yes, that I was expecting this. ADA delta went on the top now. it is performing good with that higher learning rate, but others who were performing good earlier, they maybe approximately, or they just reduced. This one that we have is Adamax. Earlier it was performing good, but now it is a low performer. So this comparison you will see when you change parameters from your model. So let me know if you all are able to observe these. Okay, code I need to share. Okay, fine. Let me check which one I shared last. Up to plotting. Okay, I have shared all the codes, I think. Which one I need to share? If you are talking about this learning rate change, I'll get it here. This is just a very basic change we are making. So here only I'll pass it in the middle. So you can just make previous one into comments and the new one you can use as per your choice. Let me know when you observe these changes and when you get this in your outcome. And later on, you can try it with other datasets like Cypher 10 dataset you can experiment with, and the yesterday's cat dog dataset also you can experiment with this. It will help you to get instant change between your accuracy values. Even you can try on just few epochs. From there only you will try to identify that what are the influence of changing optimizer in your model. I'll wait for the responses in the chat box. Once you finish this observation, just try to change learning rates and update me that which one you find good enough for this model. Thanks for the update. I'll just wait for a few more responses. Yes, sure. I'll just wait. Take your time. Just try to make changes and make observations on this. This is one important parameter that you have for hyperparameter tuning of your model. So this is a very important topic basically. You will find several detailed aspects of this, and I think on my Google Scholar profile you will find one research paper also on this topic that we have used for implementation with some indoor air pollution dataset during my PhD work. So that was based on all these optimizers, a comparison we have done over there. So maybe if your detailed reference you need, you will find in that paper also. If someone need that, I may in the meanwhile find it for you, because that may be a good reference for those who want to implement it. I remember that we have done something like that. I'm not able to locate it right now, but it should be somewhere here. So you can get some reference from that directly. Yes, here I think I can see it. Yes, this one you will find, and where we have just updated various optimizers and we could get best results with the SGD optimizer. So this was one comparative study of these kind of optimizers only. You can apply it on different types of data sets. However, detailed reference you will find in this particular paper. So this could be a good start point for the beginners, even if you are doing it with your dataset. Because in our case also, this implementation we have done on IoT sensor dataset. So this dataset basically is self-generated dataset that we used from our real hardware. Then we implemented these optimizers on that. So if you need a URL, I'll just put it right here. You can find it within this. There are few more optimization processes that you will find, but yes, for the current topic, this one is more relevant that you will find. Let me know if we
anyone else is doing this and they want to report anything on the same. In the meanwhile, yesterday I remember that someone asked me about the masking techniques also. Sir, are you connected right now? Someone asked me about masking techniques. I do not remember name of the professor.
Yes, ma'am. I'm
Okay.
connected.
Okay, great. So I have brought some links for you right here. You can try them. I think you will find good starting point from here. It includes theoretical descriptions as well as some practical approach that you can try on different data sets. So because I'll not be able to explain them in detail right here, but still you will get a starting point from here.
Okay, ma'am. Thank you. I will try this.
Okay, that's great. So these are the changes that we have seen right now with the optimizers, and this is indeed one important topic.
Ma'am, one more question
Yes,
regarding this.
yes, please.
So, for example, I'm applying this on the leaf data sets. Some leaf are infected from any disease, latest, and
Okay.
I'm calculating the mask and finding the only affected area. Is
Okay.
it possible to apply only the affected area to my model, or I have to apply only in some specific size? Either
Uh,
it will be some rectangle or square size 224 like this.
Generally, when you crop data set, it is not so good to just supply only affected area. You better crop it or mask it in such a way that entire leaf is visible in your image, because when later on you will be testing your data set, then also their entire leaf will be visible. So if your model is trained only on the certain affected area, then it will be difficult to recognize for it on the real data.
Okay. Okay, ma'am. So I have to apply for segmentation
Yes.
using my masking technique. Then after the segmentation on the leaf, I have to extract it, then apply to my model, right?
Yes, that you can try. That may
Okay, ma'am.
work. Okay. So you have obtained this data set from some online source, or you are using your own data set?
Ma'am, I have using my own data sets.
That is definitely great, because if you work on your data set, that adds more impact on your study as well.
Yes, ma'am.
And later on, maybe once you train your model, in order to benchmark your model performance, you can test or validate it against an online dataset also. That also add weightage to your study, that you designed something with your raw dataset and that works good with a already available dataset also.
Okay, ma'am.
That is a benchmarking process we recommend in your model building. Basically, that adds good value to your research papers also when you validate your model on multiple datasets.
Okay, ma'am. Thank you.
Madam, one question to you.
Yes.
In case of performance tuning of a particular model or maybe on different algorithms, I have to apply both these parameter tuning using hyperparameter technique for every learning rate as well as all the parameters you are giving for the different algorithms. Is it necessary, or you have to compare only 2-3 parameters? It is sufficient to conclude that this algorithm is best for the following data sets, because every data set has different dimensionality as well as their impact also in the number of features they are included in a particular purpose. So my question is, how do I conclude that this performance tuning issues or hyperparameter tuning?
Sir, it is always based on your requirement. We never ever consider all the hyperparameters. It is, we just start, majority of them we use as a default value only. Just few of them are required to be tweaked. We most commonly play with the learning rate values. Sometimes we add changes to the momentum values, and sometimes we turn on and off special performance parameters, such as in SGD you have Nestrov, etc. You try to turn it on and off. Not all the parameters you need to tweak every time. This is completely at what level you achieve best performance for your model, that only you have to report.
Madam, problem is that suppose I taking data from the ICUs for the patient's performance for survivability. In that case, if we have 17 to 18 features, we are applying algorithms, machine learning algorithms like decision tree, SBD, and all the decision tree, all the training algorithms of the machine learning. Now, every algorithm giving different type of performance, percentage of accuracy, loss, as well as their predictions, whatever may be. Now, if by applying this hyperparameter tuning facility, obviously you have to open every algorithm and find out what are the parameters they are using for during the time of training and whatever cases. So, how do I conclude that hyperparameter tuning in that cases? Because every algorithms are different parameters as well as their performance issues. So you are saying not every parameter should be concluded. We have to taking some parameters based on our requirement as well as performance. So my questions to you same that how do I conclude that this hyperparameter tuning will giving best achievement for the following algorithms?
Sir, this is, see, when you report your results, you have two options to state. If you have not used hyperparameter tuning, then you don't mention anything about it. You just say that we have used default parameters and then we achieved this. Whatever changes you make to these hyperparameter, only that you have to report. Like you say that all other parameters we have used with the default value, and only learning rate I have tweaked from this value to this value. And it is not even that you report only one change, because even for one hyperparameter value you conduct like hundreds of tests. So you say always that I changed this learning value maybe from 0.01 and I changed performance up to maybe 0.5, and among all the tests that we conducted in between I found 0.02 as my best value. So that we have concluded further.
Okay, madam. Thank you.
Okay.
Ma'am, my question is there is any method to optimize these parameters like SVM we are using grid CV search like that method?
Yes, that also you can apply. There are some advanced algorithms that even apply internal optimization for these parameters as well.
It is very difficult to check each and every parameters to find out.
Yes. Several people use that. Even when we are designing some basic machine learning model and or maybe ANN even. In that case, also for weight optimization, people sometimes add genetic algorithm or particle swarm optimization for internal optimization of the algorithm itself. So everything is possible. This is even a part of research, that how you create hybrid models by inserting some optimization algorithm within the existing model.
No, ma'am, in case of CNN, any deep learning model, like learning rate, number of epochs, we try to find. So instead of trying each and everything, any direct method that we can apply that can give me some optimized parameter?
Yes, that is also possible. What you do is you create a list of parameters. In that case, you give optimal values with a list of parameters. Like you provide for the learning rate, you provide 10 possible values. For other, you provide 15 or 8 or any number of possible values. Then you iterate through those values with a for loop. That is the simplest technique. Your model automatically will jump through all those combinations. It will put up all the permutations and combination, and finally it will bring out the best outcome from there itself. You will come to know the best parameters out of all the hit and trials it do on the given parameters, and that will bring you the easy option for finding the best parameter.
Ma'am, please name these methods. Which method we can use this?
See, this is a very simple method. You need not to name anything to this. This is a simple Python basic you will have. You simply iterate through multiple values, create list of values.
Okay.
Then apply for loop for that. So it will create just combination of multiple values. This is just an approach we are following, not the algorithm we are talking about.
So there is no special method for that, right?
Special method is based on advanced algorithm that you have to go with the literature, because that I have not used any time. But this simple approach I have tried several times to get best parameters out of the model. So this works every time.
Okay, ma'am. Thank you.
How to download SAHD dataset, because we want to solve. I have shared this dataset already, ma'am. This should be in your folder of day 2. This SAHD dataset is already inside that folder. For what does it mean if the argumentation may train validation accuracy is less than without argumentation? That may be a chance. Sometimes it happens when we apply wrong argumentation technique. I have shown that yesterday also with that MNIST dataset. I told you that I made hidden trials with 5-6 different argumentation techniques, but many of them were reducing my accuracy. So I just switched off few of the augmentation techniques and turned on only 2 out of 6. I turned on only 3, I think. One was a rotation angle, one was a left shift, one was right shift. So only that I used, then my model performed well. So this is about which augmentation technique is suitable for your kind of data. If a wrong augmentation technique is being applied, as we discussed yesterday, like for a bird image, you cannot flip it in opposite side, otherwise the head of the bird will be downward and legs will be on the top sides. That doesn't make any sense for a model. So which type of augmentation is good for a specific image, that only you have to choose, so that accuracy stays within your requirement. Otherwise you will have a very bad impact on the accuracy. Some people are looking forward for my email ID, so I'll put it right here in the chat box. So since this is my last session in the current FDP, if we have anything to discuss regarding whatever I have done in the previous sessions, previous 6 talks that I have delivered, we have 10 minutes for that. Anything we have to discuss, you can let me know. Otherwise, you can reach out to me using my email address that I have shared. And in order to find more information about me, you can just visit my website also. You will find everything about me as well as my firm over there. My detailed CV is also available in the about section of this website. So from there, you can find any further reference on any kind of collaboration or any kind of trainings or workshops you wish to conduct in future. So all those details you will find on the website itself. In the meantime, the house is open for the discussions on the previous topics as well as today's topic. A reference on GAN, this maybe you may need to ask some other expert right now, because I have not worked very in depth with the GAN models. So I think in your timetable also there is one expert who was expected to deliver on the GAN models also, or maybe that person could be more appropriate to answer this question.
On the behalf of Faculty Development Program on Deep Learning Applications Organizing Committee, I thank the respected FDP speaker, Dr. Jagriti Seni, for leading such an enriching and comprehensive 2-week faculty development program on deep learning applications. Your expertise has provided us with valuable sights across a broad spectrum of topics. From the very first day, where we delved into the essentials of data processing, sampling techniques, and data cleaning, to the subsequent exploration of data visualization, exploring data analysis, and data reporting, each session was incredibly informative. The theoretical overview of deep learning and CNN architecture, along with the practical task of building a CNN to classify handwritten digits using a MNIST dataset, was particularly enlightening. As we move forward, the detailed study of CNN layers, feature maps, and pooling layers, followed by the real-world task of classifying animal images from the CIFAR-10 dataset, truly enhanced our practical understanding. On the day 4, we learned valuable techniques for increasing dataset size and diversity, and applying data augmentation to improve model accuracy was a key takeaway. Finally, your deep dive into gradient descent, learning rate schedules, and optimizers combined with the practical experiments using optimizers like SGD and ADM pushed us to refine our approach to improving model performance. Your dedication to bridging theoretical concepts with the practical applications has made this FDP an immensely valuable experience. Thank you, ma'am, for guiding us through the journey. With the help of FDP speaker, I am concluding the session. Thank you all.
Thank you very much.
Thank you, ma'am.
Thank you so much, sir, for giving me this opportunity to be a part of this FDP.
Thank you, ma'am. Thank you.